Hello there and welcome to Science for Sleep, where curiosity gets comfortable, complicated science is allowed to take its time, and tonight we're going to look for something that cannot actually be seen. That sounds like an awkward assignment for a telescope. Usually when using a new telescope, the basic idea is fairly obvious. Collect light, make an image, find something interesting in the image, preferably something extremely far away, unusually bright, or shaped in a way that causes several astronomers to cancel their weekend plans. Euclid is different. The European Space Agency's Euclid Space Telescope was built, among other things, to investigate one of the largest invisible structures in the universe. Dark matter does not glow like a star. It does not shine in infrared. It does not conveniently reflect sunlight toward a camera. As far as we know, it does not interact with light in the ordinary way at all. And yet, there is a great deal of it. We know that because gravity notices things even when our eyes do not. Tonight, we're going to follow Euclid as it begins doing something astronomers have been preparing for years to do on an enormous scale. Use the shapes of distant galaxies to work out where invisible matter is concentrated. That sentence sounds a little strange when you first hear it. Imagine saying to someone, "I cannot see the object, but I can tell you where it is because of what it did to something several billion light years behind it." This would normally be an excellent way to make the person sitting next to you on a train change seats. In astronomy, however, it is a perfectly serious method. Recently, researchers working with Euclid observations demonstrated the technique using a massive galaxy cluster called a Bell 2390. Thousands of galaxies behind the cluster provided the clues. Their light had travelled across the universe, passed through the gravitational influence of the cluster, and arrived at Euclid carrying tiny distortions. Those distortions allowed scientists to reconstruct where the mass in and around the cluster was located. Most of that mass is not visible matter, it is dark matter. So when you hear a title like, "Euclid just found where dark matter really hides," we should be a little careful. Euclid has not discovered that dark matter has been secretly storing itself behind one particular galaxy while hoping nobody would notice. Dark matter is distributed throughout the universe, surrounding galaxies, filling galaxy clusters, and helping form the enormous structures that connect them. What Euclid is beginning to show us is how precisely that hidden mass can be mapped from space, over areas far larger than previous space telescopes could study in the same way. That is where tonight's story begins. Before we go any farther though, I'd love to know where in the world you're listening from tonight. Maybe you're somewhere where the sky outside is completely dark. Maybe city lights have washed away everything except the moon and a few determined stars. Perhaps you're listening in bed, on a sofa, on a late train, or while pretending that the next video definitely will not autoplay. And when you look up at the night sky from wherever you are, what do you imagine is actually there? Not just the stars you can see. Everything. The galaxies between those stars, the distant clusters beyond them, the gas between galaxies, the enormous empty-looking regions, and mixed through much of that structure, matter that has never been photographed directly. It's an odd thought. Human beings have spent thousands of years improving our ability to see the universe. We began with our eyes, then came lenses, telescopes, photographic plates, radio dishes, space observatories, infrared detectors, X-ray telescopes. Every improvement seemed to reveal something that had previously been hidden. Fainter stars appeared, new galaxies appeared, dust clouds became visible in wavelengths our eyes cannot detect. Black holes announced themselves through the matter around them. Eventually, we became very good at building machines that could observe things no human eye could ever see. Dark matter still refused to cooperate. If you're enjoying this slower journey through the universe, you can give the video a like and subscribe to Science for Sleep. It helps these long, quiet investigations reach other curious people who enjoy learning about the universe without being shouted at by a thumbnail every 12 seconds. And don't worry, there will be no exam at the end. You're also under no obligation to remain awake for all of it. In fact, considering the name of the channel, That might technically count as a failure on our part. For now, just settle in and let's look at what Euclid has actually begun to reveal. The telescope itself is sitting far from Earth, observing large areas of the sky with a combination of sharp, visible light imaging and near-infrared measurements. Its broader goal is enormous. Scientists want to study how cosmic structure developed over billions of years and how that structure relates to dark matter, dark energy, and the expansion of the universe. That means Euclid is not simply trying to take attractive pictures. It certainly does take attractive pictures. Very attractive pictures, actually. Space agencies have become remarkably good at producing images that make the rest of us briefly consider buying a telescope before remembering that professional observatories have slightly better equipment than the one currently available beside the garden furniture at the local shopping centre. But the images are measurements. Every distant galaxy has position. It has a brightness. It has a shape. It has a size. Its light contains information about distance and motion. Take enough galaxies, measure them carefully enough, and the universe stops looking like a collection of isolated objects. Patterns begin to appear. Galaxies gather in groups. Groups gather in clusters. Clusters connect through larger structures. Between them are enormous regions containing far fewer galaxies. Astronomers call this large-scale arrangement the cosmic web. Dark matter plays a major role in that web. Ordinary matter, the material that makes stars, planets, gas clouds, coffee cups, sleeping cats, and whichever device you're listening on right now, tends to collect where gravity pulls it. Dark matter contributes most of the mass in many of the structures where galaxies gather. So galaxies are useful signs. They tell us where some of the structure is, but they do not tell us everything. Suppose you walked into a dark room and someone had scattered furniture around it. You cannot switch on the light. You cannot use a torch. For reasons that are becoming increasingly unreasonable, you're also not allowed to touch the furniture. But you can roll marbles across the floor. If the marbles move in perfectly straight lines, there is probably nothing disturbing them. If several begin changing direction in similar ways, you might infer that something is affecting their paths. You still haven't seen the object. You have seen its effect. Gravity gives astronomers something vaguely similar, although fortunately with fewer overturned chairs. Mass changes the geometry of space-time. Light travelling through that geometry follows the altered path. When enough mass sits between us and a distant galaxy, the galaxy's light can be bent. Sometimes the effect is dramatic. A background galaxy can appear stretched into a bright arc. Multiple images of the same object can appear around a foreground galaxy or cluster. Under especially neat conditions, the light can form a ring. These obvious cases are known as strong gravitational lensing. Euclid has already found many examples of that kind of lensing. They are spectacular. They are also relatively rare, but another form of gravitational lensing is happening far more frequently, and it is much harder to notice. Weak gravitational lensing produces distortions so small that looking at one galaxy usually tells you almost nothing. A galaxy might naturally be oval. It might naturally be tilted. It could be irregular, stretched, lumpy, faint, or simply having a bad astronomical morning. Astronomers do not know exactly what that individual galaxy looked like before its light passed through intervening matter. So they do not rely on one. They use many, hundreds, thousands, eventually millions and far more as the survey grows. Now imagine a field full of distant galaxies, each pointing in a slightly different direction. Their natural orientations should be largely random, but if a large concentration of mass lies between those galaxies and the telescope, gravity introduces a tiny shared distortion. One galaxy does not reveal much, neither does the next. Then researchers begin combining measurements. A pattern appears. The background galaxies show a slight tendency to align around the foreground mass. The effect is extremely subtle, but statistically it becomes measurable. That pattern is called shear. By measuring it, astronomers can estimate the gravitational field responsible for it. From the gravitational field, they can reconstruct the distribution of mass. This is the important part. The method responds to mass whether that mass is bright, faint, or completely dark. Gravity does not care whether something photographs well. That makes gravitational lensing one of astronomy's most useful ways of studying dark matter. Euclid was designed to perform this kind of measurement across a huge portion of the sky. The recent work with Abel 2390 was important, partly because it showed how the process works with real Euclid observations. Abel 2390 is a massive galaxy cluster. If you were looking at Euclid's image without any additional analysis, you would see galaxies. Lots of them. Some belong to the cluster itself, others sit much farther behind it. A few foreground stars from our own Milky Way also appear in the view, which is the universe's way of making sure astronomical images never arrive with perfectly convenient labels. The scientists needed the background galaxies. Only objects behind the cluster can have their light lensed by the cluster on its way to us. So researchers had to determine which galaxies were likely behind Abel 2390, measure their shapes extremely carefully, account for galaxies belonging to the cluster that might contaminate the sample, and test whether the resulting signal survived different analysis methods. This is the less glamorous side of discovering invisible matter. Nobody presses a button labelled Dark Matter Map. There is no cheerful electronic beep. A small printer does not produce a receipt saying, "Congratulations, you have located 4.7 trillion invisible somethings." The measurement has to be built from tiny effects. Researchers compare shapes. They estimate distances. They correct biases. They test algorithms. They run simulations. Then they test things again because scientists have learned, often through painful experience, that the universe is perfectly happy to let you make an embarrassing mistake. In the Abel 239, for analysis, multiple independent methods for measuring galaxy shapes produced results that agreed well with one another. A coherent weak lensing pattern appeared around the cluster. From that pattern, scientists reconstructed the cluster's mass distribution, and most of that mass is dark matter. Think about what that means for a moment. The telescope did not photograph dark matter. No pixel in the Euclid image contains dark matter glowing purple. When you see a dark matter map shown in colour, that colour has been added to represent the reconstructed mass distribution. What Euclid actually measured was light. Light from galaxies farther away. The dark matter revealed itself because its gravity changed that light by a tiny amount before the light reached the telescope. There is something wonderfully indirect about the whole process. It's like trying to work out where someone walked across a room without seeing the person, hearing them, or finding footprints, but noticing that every hanging picture on the wall has shifted 0.5 millimeter. You would probably suspect something happened. Astronomers do roughly that, except the pictures are galaxies, and the room is a significant portion of the observable universe. The scale is where Euclid becomes especially interesting. Weak gravitational lensing is not new. Astronomers have measured it before. The Hubble Space Telescope has helped scientists study dark matter in galaxy clusters with extraordinary detail. Ground-based surveys have also mapped weak lensing across large areas. Euclid's advantage is the combination of sharp, space-based imaging and a very wide field of view. Earth's atmosphere constantly distorts incoming light. That is why stars appear to twinkle. It's charming when you're standing outside on a clear evening. It's less charming when you're trying to measure an incredibly tiny change in the shape of a galaxy, and the entire atmosphere has decided to wobble in front of your detector. Put the telescope in space and that problem disappears. Euclid can produce sharp images without atmospheric blurring, while observing a field far wider than Hubble can see at once. The researchers behind the Abel 2390 study pointed out that Euclid's field of view is about 180 times larger than Hubble's. That does not mean Euclid simply replaces Hubble. The telescopes are built for different kinds of work. Hubble is exceptionally good at looking deeply and sharply at selected targets. Euclid was designed to combine precision with scale. It is meant to survey. The Abell 2390 weak lensing observations covered less than 0.004% of the sky area planned for Euclid's full survey. Less than 0.004%. That is a demonstration, not the finished picture. Imagine being shown a few grains of sand from a beach and being told that researchers are preparing to map the coastline. The interesting part is not only what those grains contain, it is what becomes possible when the same method is applied again and again across an enormous area. As Euclid continues collecting data, astronomers will be able to study how dark matter is distributed around many galaxies and clusters, how those structures connect, and how the pattern changes across cosmic time. That matters because dark matter is not merely an extra ingredient sprinkled through the universe after galaxies formed. It is deeply connected to how structure formed in the first place. Very early in cosmic history, matter was distributed much more smoothly than it is today. Tiny differences in density existed. Regions containing slightly more matter had slightly stronger gravity. They attracted more material. Those concentrations grew. Dark matter began collecting into structures. Ordinary gas fell into the gravitational wells created by that matter. Stars formed. Galaxies developed. Clusters assembled. Over billions of years, small differences grew into the enormous network we see now. At least that is the broad picture. The details are where things become interesting. We still do not know what dark matter actually is. That fact deserves a pause because the phrase dark matter can sound much more confident than our knowledge really is. It sounds like a substance somebody has already collected in a laboratory. Perhaps it comes in a sealed container beside the nitrogen. It does not. Dark matter is the name we give to the invisible mass required to explain a wide range of gravitational observations. Something is affecting galaxies. Something is helping hold galaxy clusters together. Something bends light. Something contributes to the way large-scale cosmic structure forms. The evidence for unseen mass comes from many directions, and the simplest broad explanation is that the universe contains matter that interacts gravitationally but does not interact with light in the ordinary way. What that matter consists of is another question. There have been many candidates. Some ideas involve new kinds of particles. Others explore whether our theories of gravity need adjustment under certain conditions. Experiments on Earth have spent years trying to detect dark matter particles directly. So far, there has been no universally accepted direct detection. Dark matter remains very good at being dark. Euclid approaches the problem from another direction. Instead of waiting for a dark matter particle to interact with a detector, it measures what gravity has already done across the sky. The invisible mass may not introduce itself. Its gravitational effects do. That is why maps matter. Knowing that dark matter exists is one problem. Knowing exactly how it is distributed is another. Imagine knowing that a city contains roads but having no map. You might see cars in different places. You could watch where traffic gathers. You might infer that certain routes must exist. Eventually, though, you would want to know how the entire network connects. Dark matter maps attempt something similar on cosmic scales. Galaxies are not scattered independently through space. They sit within a structure influenced by dark matter. Large dark matter halos surround galaxies. Much larger concentrations occupy galaxy clusters. Filaments connect dense regions. Voids sit between them. Euclid's long-term survey is meant to measure this structure across an enormous volume and across billions of years of cosmic history. That means the telescope is not only asking, where is the matter? It is also asking, how did that distribution change? And that question connects dark matter to another mystery. Dark energy. Dark energy is the name used for whatever is causing the expansion of the universe to accelerate. Again, the name sounds reassuringly definite for something we understand rather poorly. Astronomy has a habit of naming a mystery and then leaving future generations to deal with the difficult part. Dark matter affects how structures grow through gravity. Dark energy affects the expansion of the universe. If cosmic expansion changes, the growth of structure changes too. So by studying where matter has collected at different periods in cosmic history, scientists can test models of both. This is why Euclid needs such an enormous survey. One galaxy cluster can teach us a great deal about that cluster. Thousands upon thousands of structures begin to tell us about the universe. Patterns become measurable, rare cases appear, small disagreements between observations and theories become easier to notice. Maybe the standard picture will continue working beautifully. Maybe Euclid will reveal tensions we did not expect. Maybe the distribution of dark matter will behave exactly as our best models predict. Or perhaps somewhere in that enormous dataset, there will be a pattern that causes a researcher to stare at a screen for a little longer than usual and say the scientific equivalent of, "Well, that's odd." Those moments are worth waiting for. For now, Euclid has shown that its eyes are capable of doing the work. Around Able 239, it measured the tiny distortions of background galaxies and used them to trace a mass distribution dominated by something we cannot directly see. The result is not the final map of dark matter, it is evidence that the mapping machine works, and when the area examined in this pilot study is compared with the area Euclid is intended to survey, the difference is enormous. The small patch becomes the interesting part precisely because it is small. It gives us a preview. Imagine having a new camera designed to photograph an entire continent in extraordinary detail. Your first successful image covers one neighbourhood. You would certainly examine the neighbourhood. You might find things there worth studying for years, but sitting in the background of every conversation would be the same thought. What happens when the rest of the map arrives? That's where we are with Euclid. We have already seen the telescope identify gravitational lenses, reveal enormous numbers of galaxies, and provide detailed views of clusters and deep fields. Now, weak lensing from real Euclid data has been used to reconstruct the invisible mass around a massive cluster. There is much more sky ahead, and there are many more structures hidden inside it. So as you settle a little more comfortably into wherever you're listening, keep one simple idea in mind. The universe you see is not the same thing as the universe that is there. The stars are real. The galaxies are real. The glowing gas, bright clusters, dusty clouds, and distant points of light are all part of the story. But light is selective. It only shows us matter that emits, absorbs, scatters, or reflects electromagnetic radiation in ways our instruments can detect. Gravity has fewer preferences. A star has gravity. A planet has gravity. A cloud of gas has gravity. And dark matter, whatever it eventually turns out to be, has gravity. Euclid uses that fact as a way into the invisible universe. Dark matter did not begin as an object anyone was searching for. It began as a mismatch. That was the uncomfortable possibility astronomers kept running into. The universe appeared to contain more matter than anyone could account for simply by adding up the stars, gas, dust, planets, and everything else that gives away its presence through light. At first, this did not look like a problem that would eventually require a dedicated space telescope. It looked more like bad bookkeeping. Astronomers would observe a collection of galaxies, estimate how much visible matter was there, calculate how gravity ought to behave, and discover that the numbers did not quite work. Perhaps some stars were too faint to see. Perhaps there was more gas between the galaxies. Perhaps the measurements were wrong. Science is full of moments like this. When an observation refuses to agree with expectation, the first conclusion is rarely, "Excellent. We have discovered an entirely new component of the universe." Usually the first conclusion is, "Let's check that again." And dark matter was checked again, then in completely different ways. The strange thing was that the missing mass problem did not disappear. It became harder to ignore. One of the earliest famous clues came from a very large gathering of galaxies called the Coma Cluster. In the early 1930s, astronomer Fritz Zwicky studied the motions of galaxies inside it. A galaxy cluster is exactly what the name suggests. a large collection of galaxies held together by gravity. That sounds straightforward until you remember that galaxies themselves are enormous objects containing billions or even trillions of stars, and a rich cluster can contain hundreds or thousands of galaxies moving through a shared gravitational environment. Zwicky looked at how quickly galaxies in the Coma cluster were moving. Then he asked a simple question. Is there enough visible mass in this cluster to provide the gravity needed to keep these galaxies together? The answer appeared to be no. The galaxies were moving too quickly. If the cluster contained only the matter astronomers could see, many of those galaxies should not have remained comfortably bound inside it. They should have been leaving. Imagine watching children spinning on a playground roundabout. The faster they move, the stronger the inward pull must be to keep them following the circular motion. Now imagine calculating the strength of that pull and finding that it is nowhere near enough. Either your calculation is wrong, or there is another force involved, or there is something providing additional mass that you cannot see. Zwicky's suggestion was that the cluster contained a great deal of unseen material. He used the German expression dunkle Materie, dark matter, a wonderfully dramatic name for what was, at the time, basically an astronomical discrepancy. But the idea did not immediately transform physics. There were plenty of reasons to be cautious. Measuring the masses of distant galaxies was difficult. Measuring their velocities was difficult. Estimating how a cluster of galaxies behaved dynamically was difficult. Astronomers were not about to rewrite their understanding of the universe because one cluster seemed heavier than expected. For decades, dark matter remained interesting, but hardly settled. Then galaxies themselves began behaving badly. A spiral galaxy, like our Milky Way, contains stars orbiting around its centre. That movement is controlled by gravity. Much of the visible light in a spiral galaxy is concentrated toward its central region, where stars are more densely packed. So if most of the galaxy's mass followed the visible light, you might expect stars farther from the centre to orbit noticeably more slowly. There is a familiar version of this in our own solar system. Mercury, close to the Sun, moves around it quickly. Earth moves more slowly. Neptune, much farther away, takes about 165 Earth years to complete a single orbit. The farther you go from the dominant central mass, the lower the typical orbital speed becomes. Of course, a galaxy is not exactly a giant solar system. Its mass is distributed across billions of stars, gas clouds, dust, stellar remnants, and other material rather than concentrated almost entirely in one central star. But the same basic gravitational logic still applies. Once you move beyond most of the visible mass, orbital speeds should decline. Astronomers measured them. They did not decline as expected. By the 1970s, observations associated especially with astronomer Vera Rubin and her colleague Kent Ford provided strong evidence that stars and gas in the outer parts of spiral galaxies were moving much faster than the visible matter alone seemed able to explain. Instead of dropping steadily with distance, the rotation speeds often remained roughly flat far beyond the bright central regions. That sounds fairly harmless. A flat graph. Not usually the beginning of a cosmic crisis. But that flat graph was saying something important. There had to be much more gravity in the outer parts of galaxies than the visible stars and gas could provide. A useful way to picture this is to imagine standing outside at night and seeing a few people walking in a large circle. You assume they are walking around a small fountain in the centre. Then you measure how quickly they are moving and realise the motion makes no sense for a small fountain. Something much larger must be affecting them. Turn on the lights, and perhaps you discover that the fountain sits in the middle of an enormous circular structure you could not see in the darkness. Astronomers had the motions, they had the visible stars. They were missing the larger structure. The simplest interpretation was that galaxies were embedded in vast halos of invisible matter, extending far beyond the bright regions seen through telescopes. That changed the picture of a galaxy. A galaxy is not merely the glowing spiral or fuzzy oval we see in photographs. The visible object sits inside a much larger gravitational structure. The bright part is almost like the lit section of a building at night. You can see the windows, you cannot see the full property boundary. The stars trace only part of what is there. For a typical large galaxy, the dark matter halo can extend well beyond the region containing most of its visible stars. That means when you look at a beautiful image of a spiral galaxy, there is something missing from the photograph. Not because the camera is poor, not because someone forgot to increase the exposure. The missing structure simply does not produce light in the way ordinary matter does. We should pause here to separate two things that are easy to confuse. Dark matter is not dark because it is ordinary material hidden behind dust. Dust can block visible light, but it interacts with radiation. We can detect warm dust in infrared wavelengths. Gas may be invisible to human eyes, but specific gases emit or absorb particular wavelengths. Cold objects can still influence or produce radiation. Black holes do not emit light from inside their event horizons, but matter falling around them can become extremely bright. Dark matter is different. As far as observations currently tell us, it does not emit, absorb or reflect electromagnetic radiation in the ordinary way. It appears to interact gravitationally. That is why the word invisible is useful, as long as we remember that invisible does not mean undetectable. We detect wind without seeing air move directly. We detect magnetic fields by watching what they do to charged particles and magnets. You can discover that someone has sat on a sofa without seeing the person if one cushion has acquired a suspiciously human-shaped dent. The effect tells you something about the cause. Dark matter is studied through effects. Galaxy rotation was one, galaxy clusters gave another. Then gravity provided an especially elegant tool. According to general relativity, mass changes the geometry of space-time. Light travelling near a concentration of mass follows that curved geometry, so its path appears bent to us. This gravitational lensing can reveal mass even when the mass itself produces no light. A galaxy cluster therefore acts as more than a collection of galaxies. It becomes a natural lens. Light from galaxies far behind the cluster travels through the cluster's gravitational field before reaching us. Sometimes the distortion is obvious. A distant galaxy may appear stretched into a long arc. The same background galaxy may appear multiple times. Under certain alignments, its light can form something close to a ring around the foreground lens. Those are strong gravitational lenses, and they are among the easiest lensing effects to appreciate because you can look at an image and immediately see that something unusual has happened. But the important detail is not simply that the image looks strange. The distortion contains information about mass. Measure how the light has been bent, and you can estimate how much matter must be present to produce that bending. Then compare that mass with the stars and gas you can observe. Once again, there is more gravity than visible matter can explain. Different measurement, same uncomfortable result. Dark matter was no longer relying on one strange galaxy cluster or one set of rotation curves. It was appearing through several independent kinds of observation. The situation became even more interesting when astronomers studied collisions between enormous galaxy clusters. One of the best-known examples is the Bullet cluster. Two galaxy clusters collided. Now, galaxy clusters contain several major ingredients. They contain galaxies, they contain hot gas, and they contain dark matter. The galaxies are separated by such enormous distances that when clusters collide, many individual galaxies pass through without directly hitting another galaxy. The hot gas behaves differently. Gas particles interact with one another. As the clusters pass through each other, this gas collides, heats up, and slows down. X-ray telescopes can observe the extremely hot gas. Dark matter, according to the standard picture, barely interacts with ordinary matter except through gravity, so most of it should pass through the collision without experiencing the same kind of drag as the gas. That gives astronomers a remarkable natural experiment. Where is the ordinary matter? Where is most of the mass? In observations of the Bullet cluster, the locations do not match. X-ray observations reveal the hot normal gas concentrated in one distribution. Gravitational lensing reveals where most of the total mass is concentrated. The mass traced by lensing lies closer to the galaxies that pass through one another and away from much of the slowed gas. It is difficult to look at that result and explain everything simply by saying that astronomers failed to notice enough faint stars. The missing mass behaves differently from the ordinary hot gas. More recent observations, including detailed work using the James Webb Space Telescope, have continued refining the mass map of the bullet cluster. The basic reason the object remains so famous is simple. The collision separates things that usually overlap. Inside an ordinary galaxy cluster, stars, gas galaxies, and dark matter occupy much of the same general region. It can be difficult to tell which component is responsible for which part of the gravitational signal. A collision shakes everything apart. The gas slows, the galaxies mostly continue. The gravitational mass distribution follows the collisionless component much more closely than it follows the hot gas. For anyone trying to understand something invisible, having nature separate the ingredients is rather helpful. It is the cosmic equivalent of opening a kitchen drawer and discovering that someone has already sorted every utensil into labelled compartments. Scientists rarely receive that kind of courtesy. The evidence did not stop with individual galaxies and clusters. Dark matter also helps explain why the universe looks the way it does on enormous scales. Look far enough across the cosmos, and galaxies are not distributed randomly like crumbs dropped over a table. They form a network. There are dense clusters, long filaments, walls containing huge numbers of galaxies, and large voids with far fewer galaxies. Computer simulations show that dark matter plays a crucial role in forming this structure. After the early universe cooled from its much hotter beginning, matter was distributed with small variations in density. Some regions were slightly denser than others. Gravity amplified those differences. Regions with more mass attracted additional matter. Dark matter, which does not interact strongly with radiation the way ordinary charged matter does, could begin building gravitational structure efficiently. Over time, dark matter collected into halos and filaments. Ordinary gas fell into those gravitational wells. Galaxies formed there. Clusters grew at the intersections of large structures. The result, after billions of years, is the cosmic web. This gives us another way to understand the phrase, dark matter was hiding in plain sight. Not because there was one dark object sitting directly in front of astronomers. It was hiding inside the behavior of almost everything they were already studying. A rotating galaxy carried evidence of it. A moving cluster carried evidence of it. A distorted background galaxy carried evidence of it. The large-scale pattern of galaxies carried evidence of it. Even observations of the early universe contained information pointing toward it. There was no need for dark matter to shine. Its gravity kept leaving fingerprints. This scale of the missing component is difficult to appreciate. Current cosmological estimates put ordinary matter at only around 5% of the universe's total mass energy content. Dark matter accounts for roughly 27%. The remainder is associated with dark energy. So even though ordinary matter makes every star, planet, person, mountain, ocean, spacecraft, biscuit, pillow, and telescope we have ever directly handled, it represents only a small fraction of the full cosmic inventory. And if we compare matter alone, rather than including dark energy, dark matter makes up most of it. That is a remarkable fact to learn from a universe that appears, at first glance, to be filled with stars. Our eyes give us a biased survey. Stars are very good at advertising. They produce enormous amounts of radiation. Galaxies filled with them can remain visible across billions of light years. A relatively small amount of hot gas can also glow strongly in X-rays. Dust can re-radiate energy in infrared. Dark matter contributes no helpful glow at all. So photographs naturally emphasize the minority component that interacts strongly with light and emit much of the matter that determines the gravitational structure. Imagine looking at a nighttime photograph of a city taken from an aircraft. You see roads because headlights follow them. You see buildings because windows are illuminated. You see stadiums, signs, bridges, airports, and parking lots. The photograph gives you real information, but the light is not the city. Most of the concrete, steel, soil, pipes, foundations, cables, walls, and infrastructure do not appear clearly. You infer the structure partly from what the lights are doing. Astronomers face something similar on a much greater scale. Stars tell us where luminous matter is gathered. Their motions tell us about the gravitational environment around them. Background galaxies tell us how space-time has been distorted between them and us. Clusters tell us where huge concentrations of mass have accumulated. No single clue has to do all the work. Together they produce a consistent picture. That does not mean every question is settled. Quite the opposite. Knowing that dark matter behaves as though it exists is not the same as knowing what it is. This is where the subject becomes slightly frustrating. We can map its gravitational influence across millions of light years and still be unable to place a dark matter particle on a laboratory bench. There are many proposed particle candidates. Some models involve weakly interacting massive particles, often shortened to WIMPs. Others involve extremely light particles such as axions. Another possibility involves particles from extensions of known physics that have not yet been detected. Scientists have built sensitive experiments underground, in laboratories, and in space to look for possible interactions. They have searched for particles created in high-energy collisions. They have looked for radiation that might be produced if certain dark matter particles annihilate or decay. So far, no candidate has received the kind of unambiguous confirmation that would allow scientists to announce, "This is dark matter." The gravitational evidence is strong. The identity remains open. There are also researchers who explore whether some observations attributed to dark matter could instead point to modifications of gravity. Perhaps our description of gravity changes at extremely low accelerations or very large distances. Modified gravity ideas have had successes in explaining certain galactic behaviors, and testing alternatives is an important part of science. But any successful alternative has a demanding job. It must explain galaxy rotation. It must explain galaxy clusters. It must account for gravitational lensing. It must fit observations of the early universe. It must reproduce the way large-scale structure grows. It must deal with systems such as colliding clusters. Changing one equation cannot simply solve one problem and quietly ignore the others. The universe has submitted a rather extensive list of requirements. The standard cosmological model, which includes cold dark matter, has done remarkably well across many of these scales. Here, cold does not mean dark matter is sitting in space wearing a tiny jumper. In cosmology, cold dark matter refers broadly to material that was moving slowly compared with the speed of light during the era when cosmic structures were beginning to form. That matters because the speed of dark matter changes the structures it produces. If dark matter particles moved extremely quickly, they would tend to smooth out smaller concentrations in the early universe. Slower dark matter can clump more effectively, allowing smaller structures to form and later combine into larger ones. When astronomers compare simulations with the universe we observe, cold dark matter provides a strong overall match to large-scale structure. But again, matching the broad picture does not mean every detail is understood. Researchers study how dark matter is distributed inside galaxies. They look at small satellite galaxies. They measure the centers of halos. They compare predicted concentrations with observed ones. They examine galaxy clusters to test whether dark matter interacts with itself more strongly than expected. Tiny disagreements can matter because different dark matter models may produce slightly different distributions. And distribution is exactly where the problem starts to connect with Euclid. For most of the history of dark matter research, astronomers were building the case from selected objects. A galaxy here, a cluster there, a lensing system, a collision, a survey covering one region of the sky. Each was useful, but there is a major difference between knowing that dark matter exists and creating a detailed statistical map of where it sits across a huge fraction of the observable universe. Suppose you're trying to understand weather. One thermometer is useful. 1,000 weather stations are better. Add satellites covering entire continents, and suddenly you're not merely measuring today's temperature. You can identify systems, patterns, movement, correlations, changes over time. Dark matter research has been moving toward that kind of scale. Instead of asking whether one galaxy contains an unseen halo, astronomers want to study enormous populations of halos. Instead of mapping one cluster, they want to measure the mass around countless structures. Instead of seeing one filament between clusters, they want to trace the network itself. And because light takes time to travel, looking farther into space also means looking farther into the past. A galaxy 1 billion light years away is being seen roughly as it was 1 billion years ago. Look much farther, and you see much earlier stages of cosmic history. A sufficiently large survey therefore becomes something more than a map. It becomes a record of how structure changed. Dark matter did not arrange itself into today's cosmic web all at once. Halos grew, clusters merged, filaments developed, galaxies moved within evolving gravitational environments. If we can map dark matter at different distances, we can compare different periods. Then scientists can ask whether structure grew at the rate predicted by our best model of the universe. That is where dark matter stops being merely a mystery about invisible mass. Its distribution becomes a test of cosmology. The amount of structure, the sizes of dark matter halos, the way matter clusters, and the rate at which those patterns change can tell scientists whether our description of gravity and cosmic expansion is working. And because dark energy affects the expansion of the universe, the growth of dark matter structure becomes one of the ways to investigate dark energy as well. Two mysteries that sound almost annoyingly similar are therefore connected through the history of cosmic structure. Dark matter helps matter gather. Dark energy, according to the standard interpretation, is associated with accelerated cosmic expansion. One shapes the gravitational framework in which galaxies grow. The other influences how the universe's expansion changes over time. To separate those effects, scientists need very large amounts of precise data. The irony is that the hidden universe can be studied only by observing the visible universe with extraordinary care. Every galaxy becomes a measurement. Its position matters, its apparent shape matters, its distance matters. The orientation of millions of neighbouring galaxies matters. A tiny distortion that would be meaningless in one object becomes useful when repeated across a huge population. That is why dark matter had, in one sense, been hiding in plain sight. Astronomers had been photographing the evidence for generations. It was present in the stars moving too quickly around galaxies. It was present in clusters whose visible contents could not provide enough gravity. It was present in background galaxies stretched by unseen mass. It was present in the separation between gas and gravitational mass after cluster collisions. It was present in the enormous web-like distribution of galaxies across the universe. The darkness was never completely silent. We simply had to learn which effects to measure. And once astronomers knew where to look, another limitation became obvious. The sky is very large. Weak gravitational lensing is extremely subtle. Cosmic structure spans billions of light years. Understanding its evolution means observing enormous numbers of galaxies across enormous distances while measuring their shapes with exceptional precision. That is not a job for a telescope designed to stare deeply at one small patch and then move carefully to another. It calls for an observatory built around scale, one that can see a large area at once, one that can work above Earth's atmosphere, where tiny galaxy shapes are not blurred by constantly moving air. One that can combine visible and infrared observations to study billions of galaxies, and one that was designed from the beginning with the dark universe as its main assignment. Which brings us back to the spacecraft now doing exactly that work, because after nearly a century of following dark matter through the motions and distortions it leaves behind, scientists finally have an instrument built to turn those clues into something much larger. Its name is Euclid. And if you were going to build a telescope whose job involves measuring the geometry of the universe, there are worse people to name it after than the mathematician whose work helped define geometry for more than 2,000 years. The Euclid spacecraft is not especially enormous by the standards of modern observatories. Its main mirror is 1.2 meters across. That is impressive, certainly, but it is smaller than Hubble's 2.4 meter primary mirror and much smaller than the 6.5 meter mirror aboard the James Webb Space Telescope. So Euclid's main advantage is not that it has the biggest eye in space, it has the right eye for a very particular job. Euclid was designed to look at large areas of sky quickly, repeatedly, and with enough precision to measure tiny changes in the shapes of distant galaxies. Those galaxy shapes can then be used to trace the gravity of matter between the galaxies and us, including matter that produces no detectable light. In other words, Euclid does not need to see dark matter. It needs to see what dark matter does. That sounds simple until you consider the scale involved. A telescope can take an exceptionally detailed image of one distant galaxy and teach us a great deal about that galaxy. It can look at a star-forming region, examine a planet's atmosphere, study a supernova, or stare into a tiny patch of sky for days and reveal extremely faint objects. Euclid has a different kind of ambition. It wants statistics, lots of statistics. It needs huge numbers of galaxies because the effect it is looking for is so small that one galaxy cannot reliably reveal it. The natural shape of a galaxy is messy. Some galaxies are circular, some are oval, some are spiral, some are stretched. Some have been distorted by interactions with neighbouring galaxies. Some look neat and symmetrical. Others look as though someone began assembling a galaxy, became distracted halfway through, and decided that was probably good enough. If Euclid measures one slightly elongated galaxy, there is no way to know, simply from that shape, whether gravity stretched its image or whether the galaxy has always looked like that. Measure millions of galaxies, however, and a different possibility appears. The random orientations begin averaging out. Tiny shared distortions remain. Those distortions can reveal the gravitational influence of matter along the path that the light travelled. The more galaxies you have, the better the statistics become, and Euclid was built with exactly that requirement in mind. ESA launched the spacecraft on July 1st, 2023, aboard a SpaceX Falcon 9 rocket from Cape Canaveral in Florida. From there, Euclid travelled roughly 1.5 million kilometres away from Earth toward a region known as the Second Sun-Earth Lagrange point, usually shortened to L2. If L2 sounds familiar, there is a good reason. The James Webb Space Telescope operates around the same general region. L2 is useful because the Sun, Earth and spacecraft can remain arranged in a fairly consistent direction relative to one another. That makes it easier for a telescope to keep the Sun behind its protective shielding, while maintaining a stable thermal environment for sensitive observations. Euclid does not simply park motionless at one invisible point in space. It follows a large orbit around the L2 region while moving around the Sun together with Earth. From the telescope's perspective, the bright Sun remains safely on one side, while much of the darker sky remains available on the other, and for Euclid, stability matters enormously. Imagine trying to measure the exact shape of a distant galaxy. Now imagine that the galaxy is so faint that its light has travelled for billions of years before reaching your camera. The distortion you want to measure may change its apparent shape by only a few %. Your telescope therefore needs to know whether that tiny change came from gravity in the universe, or from something considerably less exciting, such as a detector problem, a temperature shift, a slight movement in the spacecraft, or an optical imperfection. A tiny instrumental distortion can pretend to be a cosmic signal. Astronomers are generally not pleased when their telescope invents new physics. Euclid therefore has to remain extremely well controlled. Its optical system has to be understood precisely. Its detectors have to be calibrated. The way the telescope turns, settles, observes and moves to the next field has to be managed carefully. Even variations that would be insignificant for an ordinary photograph can matter when the goal is to measure galaxy shapes accurately enough to reconstruct invisible mass. The spacecraft itself is about 4.7 meters tall and around 3.7 meters across. It contains two main sections. There is a service module, which handles practical spacecraft jobs such as power, communication, data processing, propulsion, thermal control and pointing. Then there is the payload module containing the telescope and its scientific instruments. The distinction is slightly like separating the eyes and brain of an observatory from everything needed to keep the rest of the body alive. The scientific instruments may get most of the attention, but they are not terribly useful if the spacecraft cannot point at the sky, regulate its temperature, store its observations, or send the data home. Euclid's 1.2-meter telescope collects incoming light and directs it through an optical system that separates visible light from near-infrared light. The two portions then go to two different instruments. They are called VIS and NISP. Astronomers do enjoy an acronym. VIS is the Visible Light Imaging Instrument. Its main job sounds almost ordinary. It takes pictures. But these are not ordinary pictures. VIS was designed to produce extremely precise images of galaxies so that researchers can measure their apparent shapes. Its detector contains more than 600 million pixels. More specifically, the focal plane uses 36 CCD detectors, producing an enormous image with about 609 million pixels. This is the instrument doing much of the delicate shape measurement needed for weak gravitational lensing. Each exposure covers about 0.57 square degrees of sky. That may not sound large. Square degrees are not exactly the measurement most of us use when discussing the view from the bedroom window. For comparison, the full moon covers an area of roughly 0.2 square degrees in the sky, so Euclid's field of view covers an area several times larger than the apparent area of the full moon in a single pointing. That is unusually wide for a space telescope capable of producing images sharp enough for precise galaxy-shaped measurements, and that combination is essential. Sharpness without a wide view would make the survey painfully slow. A wide view without sufficient sharpness would provide huge numbers of galaxies whose shapes could not be measured accurately enough. Euclid needs both. This is one reason comparisons with Hubble or Webb can be misleading. People naturally want to know which telescope is better. Astronomy does not work quite like buying a television. A telescope designed to observe a tiny region in extraordinary depth may be better for one question. A telescope with a very large mirror may be better at detecting extremely faint targets. A wide-field telescope may be better at studying huge populations. Euclid was optimized for a survey. Its strength is the combination of image quality, stability, field of view, and the ability to repeat the same carefully controlled measurement across enormous areas of sky. VIS handles the visible light side of that task, but measuring shape is only part of the problem. Suppose Euclid detects 1,000 galaxies in one image. Some may be relatively nearby, others may be several billion light-years away. If you want to construct a three-dimensional map of cosmic structure, knowing where a galaxy appears on the sky is not enough. You also need an estimate of how far away it is, otherwise everything gets flattened into a two-dimensional photograph. Imagine looking out across a city at night. You can see hundreds of lights. Without any distance information, a dim light might be a small lamp nearby or a very bright light much farther away. The picture tells you direction. It does not automatically give you depth. That is where Euclid's second instrument becomes important. NISP stands for Near-Infrared Spectrometer and Photometer. It examines the universe at near-infrared wavelengths, beyond the red edge of human vision. NISP can operate in imaging mode and spectroscopy mode. Its imaging observations use several near-infrared filters. By comparing how bright an object appears through different wavelength ranges, scientists can estimate properties including the object's redshift, and therefore obtain information about its distance. Redshift occurs because the universe is expanding. Light travelling through expanding space has its wavelength stretched. For distant galaxies, spectral features that originally appeared at shorter wavelengths are shifted toward redder wavelengths by the time the light reaches us. The greater the cosmological redshift, broadly speaking, the farther back into cosmic history we are seeing. There are important details and complications, naturally. There are always details and complications. Astronomy would be a very short profession otherwise. But redshift gives researchers a way to arrange galaxies not just across the sky, but through cosmic distance and time. NISP also performs slitless spectroscopy. Ordinary spectroscopy often uses a slit to isolate one object before spreading its light into a spectrum. Euclid needs to study enormous numbers of galaxies, so NISP can disperse the light of many objects across the field simultaneously. Instead of only recording how bright a galaxy is, spectroscopy breaks its light into wavelengths. Specific features in that spectrum can reveal a more precise redshift. That helps astronomers determine how galaxies are distributed through three-dimensional space, so the two instruments have closely connected jobs. VIS says, in effect, what shape does this galaxy appear to have? NISP helps ask, how far away is it? Repeat those questions across huge numbers of galaxies, and Euclid begins building something much more useful than a collection of attractive images. It creates a statistical description of the universe. The telescope's main survey is intended to cover around 14,000 square degrees of sky, roughly a third of the entire celestial sphere. Why not the whole sky? Because parts of the sky are not equally useful for this particular experiment. Our own Milky Way gets in the way. If Euclid looks toward the plane of our galaxy, there are enormous numbers of foreground stars along the line of sight. There is also dust. Those stars and dust make it harder to measure distant galaxies behind them. The solar system creates complications too, because observations closer to the plane of the planets can contain more foreground contamination. So Euclid concentrates much of its wide survey on regions where distant galaxies can be measured more cleanly. The goal is not to photograph every direction simply for completeness. The goal is to build the cleanest, enormous cosmological dataset possible. Even then, the amount of information involved is difficult to picture. A single Euclid VIS image contains hundreds of millions of pixels. The mission repeatedly collects visible images, infrared images, and spectral measurements. Those observations have to be calibrated and processed. Objects have to be identified. Stars need to be distinguished from galaxies. Galaxy shapes need to be measured. Distances need to be estimated. Instrumental effects have to be corrected. Different observations have to be connected with data from ground-based telescopes. The final scientific product depends as much on data processing as it does on the hardware sitting at L2. This is not a telescope taking photographs for 6 years and eventually arriving home with an unusually large holiday album. Every observation enters a huge processing system. The Euclid Consortium includes thousands of scientists, engineers, software specialists, and researchers working across many institutes and countries. Their job includes turning raw detector measurements into data that can be used for cosmology. That sounds less exciting than launching a rocket. It is also where an enormous amount of the science happens. Consider something as basic as measuring a galaxy's shape. The detector records light. But before a researcher can say that the galaxy has been stretched slightly by gravitational lensing, they have to understand how Euclid's own optics would change the appearance of that galaxy. Every telescope has what astronomers call a point spread function. Even a perfect point of light does not appear as a mathematically perfect point in an image. The telescope's optics and detector spread that light into a small pattern. For ordinary astronomy, that may simply affect image sharpness. For weak lensing cosmology, you need to model it extremely accurately because you are searching for tiny distortions in galaxy shapes. If your optical system stretches images slightly to the left and you fail to correct for it, congratulations. You have just discovered a large concentration of dark matter that exists only inside your telescope. This is not considered ideal. Calibration therefore becomes part of cosmology. The mission has to understand its own vision before it can use that vision to understand the universe. Euclid also observes fields using multiple exposures rather than relying on a single photograph. The spacecraft shifts its pointing slightly between observations. This strategy helps deal with gaps between detector elements and improves the final coverage. It also provides repeated measurements that can help reconstruct a more complete image. There are engineering reasons behind almost every part of the observing sequence. A detector cannot be infinitely large. Electronics generate heat. Spacecraft pointing is not instantaneous. Data storage has limits. Communicating enormous datasets across 1.5 million kilometers takes time. Survey design becomes a balancing act between depth, area, precision, calibration, and the finite length of the mission. Spend too long looking at each field and you obtain exquisite detail over a small region. Move too quickly and you cover enormous areas without collecting enough light. Euclid sits between those extremes because its main questions require both scale and precision. Alongside the wide survey, the mission also observes much smaller deep fields. These regions receive considerably more observing time. Repeated observations allow Euclid to reach fainter objects and provide a deeper view than the main survey. The deep fields also give scientists valuable opportunities to test measurements, study changes over time, and examine populations that are harder to detect in the wider survey. Again, there is a trade-off. Most of the sky gets the broad survey treatment. Selected regions get much deeper attention. Astronomers have essentially given Euclid two assignments: look everywhere useful, and occasionally stare. The first major public data release in March 2025 gave researchers a taste of the scale involved. That quick release covered just over 63 square degrees of observations, including Euclid's deep field regions, and contained roughly 26 million detections. And even that was not the main cosmology dataset the mission was ultimately built to produce. It was an early release from a survey that is intended to become vastly larger. This is worth remembering whenever a new Euclid image appears online. A particularly beautiful galaxy may receive attention. An unusual gravitational lens may become news. A cluster may look spectacular. But the mission's deepest scientific power does not necessarily come from the most dramatic individual object in an image. It comes from accumulation. Galaxy after galaxy after galaxy. Millions becoming hundreds of millions. Measurements covering different regions of space. Measurements covering different periods of cosmic history. The ordinary-looking objects matter because there are so many of them. One person crossing a street tells you almost nothing about a city's traffic. Watch thousands of streets for months and you can begin understanding the network. Euclid is doing something comparable with galaxies. Their shapes tell researchers about gravitational lensing. Their positions tell researchers how galaxies cluster. Their redshifts help place them at different distances. Taken together, those measurements let cosmologists test how structure developed as the universe expanded. This is where Euclid's two main cosmological techniques begin to complement one another. One involves weak gravitational lensing. That is the tiny distortion of background galaxies caused by matter between those galaxies and us. The other involves the way galaxies are distributed through space. Matter does not cluster randomly. Gravity creates patterns. By measuring those patterns at different cosmic times, researchers can study how structure grew. Both methods are sensitive to the underlying cosmology. Both help test the roles of dark matter, dark energy, and gravity, and both become much more powerful when applied to an enormous survey. You may notice something interesting here. Euclid is supposedly a mission about the dark universe, but almost everything aboard it measures light. There is no dark matter sensor hanging from the side. There is no detector that sounds an alarm when a dark matter halo passes beneath the spacecraft. Euclid photographs galaxies. It measures infrared light. It records spectra. It determines positions and shapes. Everything begins with ordinary photons arriving at the telescope. The darkness appears later, in the relationships between those measurements. That is really the cleverness of the mission. Dark matter does not have to cooperate. It only has to possess gravity. The telescope looks at light from distant galaxies that have spent billions of years travelling across space. During that journey, the light passes through an uneven universe. There are galaxies along the route, groups of galaxies, clusters, filaments, large concentrations of dark matter, regions containing much less matter. Every gravitational field contributes a tiny amount to the geometry through which that light travels. By the time the photons reach Euclid, they are carrying information about the intervening structure. The difficulty is extracting it. Weak lensing is called weak for a reason. Most background galaxies do not appear as obvious giant arcs. The distortion may be tiny. You cannot point to one ordinary galaxy and confidently declare that its slight oval shape was produced by a dark matter halo halfway between here and there. Instead, researchers use populations. They look for statistical alignments. If thousands of background galaxies show a subtle pattern around a region of sky, that pattern can reveal the gravitational field. Then the gravitational field can be converted into a map of mass. Visible and invisible matter both contribute. Compare the mass map with observations of luminous matter, and the hidden component begins to emerge. This is exactly why Euclid needs so many galaxies. The mission is expected to measure the shapes of more than 1 billion of them. One slightly stretched galaxy is ambiguous. 1 billion galaxies become a cosmological experiment. That also explains why putting Euclid in space was so important. Ground-based telescopes can survey huge areas, and they are essential partners in this work. But Earth's atmosphere distorts incoming light. Air moves, temperature changes, turbulence bends light by tiny amounts before it reaches a telescope. That is why stars twinkle. The stars themselves are not flashing politely at us from hundreds of light years away. The atmosphere is changing the path of their light. For weak lensing, that atmospheric distortion is something astronomers must model and remove extremely carefully. Euclid avoids the atmosphere altogether. From space, its visible light instrument can produce stable, sharp images across a wide field. Ground-based observatories then add other measurements, particularly colours at wavelengths Euclid does not cover, helping researchers estimate galaxy redshifts more accurately. So even a space telescope designed for a particular cosmological mission becomes part of a much larger network. No telescope does everything. Euclid provides the wide, sharp, space-based imaging and near-infrared data. Other observatories contribute complementary measurements. Then computers on Earth combine enormous catalogues into something scientists can actually analyse. This process will continue for years. The spacecraft surveys, the data comes down, the instruments are calibrated, images and spectra are processed, catalogues grow. Researchers test the measurements against simulations. Systematic errors are hunted down. New maps are created. Some results will confirm what cosmologists expected, others may not. And the unexpected ones will receive a great deal of attention, followed almost immediately by someone asking whether the detector was behaving properly that day. That caution is necessary because Euclid is trying to test a model of the universe with measurements whose precision would have been extraordinary only a few decades ago. The standard cosmological model has been remarkably successful. It describes a universe containing ordinary matter, dark matter, and dark energy. It explains a great deal about cosmic structure and expansion. But the two dark components in its name remain poorly understood. We infer them from effects. We describe their behaviour mathematically. We can estimate how much of the cosmic inventory they represent. Yet we still do not know the physical identity of dark matter, and we do not know what dark energy fundamentally is. Euclid was built because increasing the amount and precision of cosmological data gives us a chance to push harder on those questions. Perhaps dark energy behaves exactly like the simplest model predicts. Perhaps it changes over cosmic time. Perhaps measurements of structure reveal something unexpected about gravity. Perhaps dark matter distributions contain clues to the properties of the particles involved. Or perhaps Euclid will make the existing picture stronger, and leave theoretical physicists the slightly awkward task of explaining why a model containing two major ingredients we cannot identify works so well. Any of those outcomes would be interesting. And this brings us to a useful point about the telescope's name. Euclid the mathematician is associated with geometry. Euclid the spacecraft studies geometry on the largest possible scale, not geometry in the sense of solving for the missing angle in a triangle while remembering something unpleasant about school. The geometry here is space-time itself. Mass alters it. Light travels through it. Cosmic expansion changes the distances between large structures. By measuring how galaxies appear and where those galaxies sit across billions of light years, Euclid turns geometry into a tool for testing the contents and history of the universe. The telescope is therefore not simply making a map of objects, it is measuring relationships, the location of one galaxy relative to another, the distortion of one population behind a concentration of mass, the statistical distribution of galaxies at different distances, the way those patterns change as we look farther back in time. From those relationships, researchers can reconstruct something that no normal camera can photograph directly. The underlying structure of matter. This was the reason for building Euclid in the first place. Dark matter had already revealed itself through galaxy rotation, cluster dynamics, gravitational lensing, colliding clusters, and the large-scale structure of the universe. Astronomers did not need another telescope merely to tell them that something invisible was probably there. They needed a way to measure where it was on a scale large enough to turn isolated clues into a cosmological map. Euclid provides that scale. Its mirror collects the light. VIS measures the galaxies with extraordinary precision. NISP helps determine how far away they are. The wide survey provides the numbers. Space provides the stable view, and years of observations provide the depth in cosmic time. But the telescope cannot simply look at a field of galaxies and identify the dark matter sitting between them. The crucial step still depends on an idea Einstein gave physics more than a century ago. Mass changes the path of light, and that is where gravity becomes a lens. Not a lens made of glass. Not something you could pick up, clean with a cloth, accidentally leave fingerprints on, and then spend 10 minutes wondering why everything looks slightly foggy. A gravitational lens is simply mass changing the path that light follows through space. The important word there is mass. Stars can do it, galaxies can do it, galaxy clusters can do it, gas can do it, dark matter can do it. Gravity does not ask whether the material producing it is visible. That makes gravitational lensing unusually valuable when the thing you want to study happens to be dark matter. To understand how Euclid uses this effect, imagine a very distant galaxy. Its stars are producing light in every direction. A tiny fraction of that light begins travelling toward the region of space that will eventually contain Earth, Euclid, and astronomers trying to make sense of the whole arrangement. The journey may take billions of years. For most of that time, nothing particularly dramatic has to happen. The photons travel through space. They pass enormous empty regions. They move near galaxies. They cross the large-scale structure of the universe. Eventually, some of that light passes near a concentration of matter. Perhaps there is a galaxy in the foreground. Perhaps an entire galaxy cluster. The light does not hit the object. It passes nearby. But the path changes. According to Einstein's general theory of relativity, matter and energy affect the geometry of space-time. We often simplify this by saying that mass bends space-time. Light then follows the geometry through that curved region. From our perspective, the light appears to have been deflected. This is gravitational lensing. Einstein was not the first person to imagine that gravity might affect light. Ideas about gravitational deflection existed earlier, but general relativity provided the modern explanation and a specific prediction for how strongly light should bend near a massive object. One of the famous early tests came during the solar eclipse of 1919. Astronomers observed stars whose apparent positions in the sky lay close to the sun during the eclipse. Normally, the sun's brightness would make those stars impossible to see from Earth during the day. The eclipse blocked the bright solar surface, allowing their positions to be measured. Their light had passed through the gravitational field near the sun. The stars appeared slightly displaced from where they would normally be seen. The measurements became famous as evidence supporting Einstein's description of gravity. At the time, bending starlight around the sun was an extraordinary test of a new theory. Today, astronomers use the same basic effect to map matter across enormous distances. Science does occasionally move from, "Can we detect this at all?" to, "Let's use it to survey billions of galaxies." The universe has had plenty of time to provide larger lenses than the sun. A galaxy contains far more mass. A cluster containing hundreds or thousands of galaxies contains far more again. Place one of those structures between us and a more distant source, and the effect can become dramatic. Suppose a distant galaxy sits almost directly behind a massive foreground galaxy. Light from the background object can travel around different sides of the foreground mass. Those paths are bent toward us. Instead of seeing the background galaxy in its normal form, we might see it stretched. In the right alignment, it can form a ring around the foreground object. This is called an Einstein ring. Sometimes the alignment is less neat, and the background galaxy appears as several bright arcs. Sometimes multiple images of the same source appear. You can look at an astronomical photograph and see what appear to be several separate objects, only for detailed analysis to reveal that they are copies of the same distant galaxy, whose light reached us along different paths. And gravity has effectively rearranged the image. This is strong gravitational lensing. And strong lensing has one major advantage: it looks like lensing. A giant curved arc around a galaxy cluster is not especially subtle. Neither is a nearly complete glowing ring. You do not need to be told that the image is behaving strangely. Something has taken an object that should look roughly like a galaxy and turned it into a luminous banana. Astronomers then have the more difficult task of working out exactly what distribution of mass caused the distortion. Because that is the useful part. The lens is not only creating an interesting image, its effect tells researchers about the matter producing the gravitational field. If you know the positions of the foreground lens and background source, estimate their distances, and measure how the background light has been distorted, you can construct models of the mass in the lensing object. Some of that mass may be visible stars, some may be gas. A great deal can be dark matter. This is one reason gravitational lensing became such a powerful part of dark matter research. It measures gravity directly through its effect on light. You do not have to assume that mass perfectly follows the visible stars. You let the lensing signal tell you where the gravitational mass is. But strong lensing alone cannot do the entire job Euclid was designed for. Strong lenses require fairly special alignments. The source, lens, and observer need to line up closely enough, and the foreground mass has to be strong enough to create those obvious arcs, rings, and multiple images. That happens often enough to be scientifically valuable, but not everywhere. Euclid's much larger dark matter map relies heavily on an effect that is happening far more widely: weak gravitational lensing. The name makes it sound like strong lensing's disappointing younger relative. It is not. Weak lensing is simply much harder to see in any individual galaxy. Imagine that a background galaxy would naturally appear almost circular. Light from that galaxy travels through a region containing foreground matter. The gravitational field slightly alters the paths of different light rays. By the time they reach the telescope, the galaxy may appear a little stretched, not into a huge arc, not into a ring, just slightly more elliptical. That is enough to contain information. Unfortunately, there is an immediate problem. Galaxies are not born circular for the convenience of cosmologists. They come in different shapes. A galaxy may already be elliptical. It may be tilted toward us. It may contain a bar. It may have spiral arms. It may have interacted with a neighbouring galaxy. Some look elegant, some look disturbed. Some look as though gravity had several ideas and refused to choose between them. So when Euclid observes one slightly stretched galaxy, it cannot simply say, dark matter did that. Perhaps dark matter did contribute. Perhaps the galaxy looked that way before its light began the journey toward us. There is no photograph available showing the unlensed version for comparison. This is why weak gravitational lensing becomes a statistical measurement. Instead of trusting one galaxy, astronomers use many. Imagine looking at 100 tiny oval marks scattered across a sheet of paper. Their directions are random, some lean left, some lean right, some point upward. There is no obvious pattern. Now imagine gently stretching the entire sheet sideways. Every oval changes slightly. The original directions were random, but the stretch adds a small shared tendency. Looking at one oval would still tell you almost nothing. Looking at all 100 allows the pattern to emerge. Weak lensing works in a similar way. The natural orientations of distant galaxies vary. A foreground distribution of matter introduces a slight coherent distortion. Astronomers call part of this effect shear. Shear changes apparent galaxy shapes in a preferred pattern. Around a large concentration of mass, background galaxies tend to be stretched tangentially around that concentration. The effect on each one may be extremely small. Average enough galaxies together and the random natural shapes begin to cancel. The shared lensing distortion remains. That is the signal Euclid can measure. And the distortions involved really are small. ESA describes weak lensing shape changes as being on the order of a few percent. A few percent is not much when you're looking at distant galaxies that may already be faint, small, irregular, and only a handful of pixels across in less capable images. This is why the quality of Euclid's visible light observations matters so much. The telescope has to distinguish a real cosmic distortion from everything else that might alter the apparent shape. Its own optics can affect an image. Its detector can introduce effects. Spacecraft pointing matters. Calibration matters. The distance to the galaxy matters. Even neighbouring objects can complicate the measurement. And once you have solved those problems, the universe provides a few more, very considerate of it. One is called intrinsic alignment. Galaxies are not necessarily oriented completely independently of their surroundings. Galaxies that formed within the same large-scale gravitational environment can have shapes or orientations that are physically correlated. That creates a pattern that can resemble part of the weak lensing signal, even though it was not caused by light being bent on the way to us. Researchers therefore need models for both the lensing effect and the ways galaxies themselves may be aligned. Then there is the question of distance. Suppose you observe a concentration of matter in the foreground. Behind it sits one distant galaxy. Much farther behind it sits another. The two light paths do not encounter exactly the same geometry. The amount of lensing depends partly on the distances between observer, lens and source. That means a two-dimensional image of the sky is not enough for Euclid's full mission. Researchers also need to estimate how far away the source galaxies are. That is where the near-infrared measurements we met earlier become part of the lensing experiment. Combine galaxy shapes with distance information, and astronomers can begin separating structures at different periods of cosmic history. Instead of asking only where matter appears across the sky, they can ask where that matter lies along our line of sight. This technique is often called weak lensing tomography. Tomography may sound familiar from medical imaging. A CT scan uses measurements from different directions to reconstruct information about the interior of a body. Nobody is putting the universe into a scanner, which would require paperwork well beyond ESA's current budget. But the basic idea of reconstructing hidden structure from indirect measurements is similar. Galaxies at different distances provide layers of information. A relatively nearby background galaxy has travelled through a certain amount of foreground structure. A much more distant galaxy has travelled through additional structure. By comparing lensing patterns for galaxies grouped at different redshifts, researchers can reconstruct how matter is distributed at different distances. Distance also means time. The farther away we look, the older the light is. So a three-dimensional dark matter map also becomes a record of how cosmic structure changed over billions of years. This is where gravitational lensing becomes much more than a clever way to say dark matter exists. Astronomers already had extensive evidence for that. Euclid can use lensing to examine where matter gathers, how strongly it clusters, and how those patterns evolved while the universe expanded. There is another form of weak lensing that is especially important on very large scales: cosmic shear. Instead of concentrating on the lensing around one obvious foreground cluster, cosmic shear measures the subtle pattern produced by the entire intervening distribution of matter across broad regions of sky. Every distant galaxy's light has travelled through a universe containing structure. There are dense regions, there are underdense regions, there are dark matter halos, there are filaments, there are galaxy groups and clusters. All of them can contribute small gravitational deflections. The final shape measured by Euclid contains the accumulated effect of that journey. One galaxy cannot tell you which structures contributed. A huge population can reveal statistical patterns in the matter distribution. That is why billions of galaxies are useful. With enough sources, researchers can calculate correlations between the apparent shapes of galaxies separated by different angles on the sky. Those correlations depend on the distribution of matter between us and them, and the distribution of matter depends on how structure formed. So the tiny ellipticity of a distant galaxy can eventually become part of a test of the universe's history. The scale difference is almost ridiculous. An astronomer measures a small change in the apparent shape of something perhaps billions of light years away. That measurement enters a catalogue. Millions of other measurements join it. The statistics reveal how matter is clustered across enormous regions. Those clustering patterns then help test models of dark matter, gravity, cosmic expansion, and dark energy. All because some galaxies look very slightly squashed. Science sometimes has an impressive ability to extract large conclusions from deeply inconvenient measurements. Gravitational lensing also does something else that makes it especially useful. It does not care what kind of matter causes the gravity. Suppose a galaxy cluster contains stars, hot gas, cold gas, black holes, planets, dust, and dark matter. Lensing responds to the total mass distribution. A mass map reconstructed from lensing therefore traces all matter along the relevant line of sight. Researchers can then compare that map with observations of ordinary matter. Stars can be mapped through visible and infrared light. Hot gas can be studied in X-rays. Other wavelengths reveal other components. If the gravitational mass extends far beyond the visible material, or peaks somewhere different from the ordinary matter, that tells astronomers something important. This is how lensing helped turn dark matter from a calculation problem into something that could effectively be mapped. Not photographed, mapped. The distinction matters. When you see a dark matter image with purple, blue, or pink clouds surrounding galaxies, those coloured regions are usually not actual light emitted by dark matter. The colour represents a reconstructed mass distribution. Researchers take gravitational information and overlay it on an astronomical image so we can see where the inferred mass lies. Dark matter has not suddenly become purple. It has shown terrible commitment to branding and continues to provide no visible colour at all. The map is a visualisation of gravity, and creating that map is not as simple as drawing a blob around every galaxy. The foreground and background objects have to be separated. Researchers need to know which galaxies lie behind the lens. A galaxy belonging to the lensing cluster itself cannot be distorted by that same cluster in the same way as a distant source behind it. Include too many cluster members in the background sample, and the lensing measurement gets diluted. Distances therefore become important again, so do large numbers, and careful calibration, and models, and testing those models against independent methods. This brings us back to Euclid's particular strengths. Its visible light camera provides sharp shape measurements over a very wide field. Its near-infrared instrument contributes information that helps determine galaxy distances. Ground-based observations add additional wavelengths. Together, those measurements allow scientists to identify huge populations of background galaxies and study their tiny distortions. Euclid can do this not only around one cluster, but eventually across a large fraction of the extragalactic sky. The full idea is easier to appreciate if we begin with one cluster. Picture a large galaxy cluster in the foreground. The cluster itself contains hundreds of galaxies. Between those galaxies is extremely hot gas. Surrounding and extending beyond much of the visible structure is a large dark matter halo. Behind the cluster sit thousands of more distant galaxies. Their light travels toward us. As that light passes through the gravitational environment of the cluster, its path changes slightly. Euclid observes the resulting galaxy shapes. Researchers select the background galaxies. They measure their ellipticities. One galaxy points this way, another points that way, another looks almost circular. Nothing dramatic happens when you inspect them individually. Then the measurements are combined. A pattern becomes visible. The galaxies show a slight tangential alignment around the cluster. The farther you move from the center, the pattern changes. From that shear signal, researchers can estimate how mass is distributed. Now place the visible image beside the reconstructed mass map. The bright galaxies mark some of the ordinary matter. The lensing map shows something much larger. The cluster is not merely the stars you can see. Most of the gravitational mass sits in the invisible component. That is what researchers demonstrated with Euclid observations of Abell 239O. And the result is especially useful because this is precisely the type of measurement Euclid is expected to perform on much larger scales. Abell 239O is a very massive galaxy cluster located billions of light-years away. Euclid observed it during the mission's early release observations program. The image contains the cluster, foreground stars in our own Milky Way, and enormous numbers of galaxies at various distances. Some of the galaxies behind Abell 239O are visibly affected by strong gravitational lensing. Bright arcs appear around the cluster. Those are useful. But researchers also examine the far less obvious weak lensing signal. They selected background galaxies and measured their shapes. The analysis used independent approaches to check that the result was not merely an artifact of one particular measurement method. The galaxy shapes showed the expected coherent pattern. From that pattern, the researchers reconstructed the mass distribution around the cluster. The map was dominated by dark matter. This was not the first time weak gravitational lensing had been used to map a galaxy cluster. Hubble and other observatories had already demonstrated that the method works. The interesting part was what Euclid could do differently. Field of view. Euclid can see a much larger area of sky in one observation than Hubble, while still producing the sharp, space-based imaging needed for precise weak lensing work. In the 2026 Abell 239O result, the Euclid Consortium noted that Euclid's field of view is about 180 times larger than Hubble's. That matters because galaxy clusters are not isolated balls of matter with neat edges. Their dark matter halos extend outward. They sit within larger cosmic environments. They connect to surrounding structures. A wider image lets researchers measure the lensing signal far from the bright cluster center. That can help trace mass beyond regions where previous narrow-field observations had less coverage. And even this impressive observation represents a tiny fraction of what Euclid is intended to do. The Abell 239O area used in the weak lensing pilot study covers less than 0.004% of the sky area planned for Euclid's full survey. That number is worth sitting with. Less than 0.004%. It is the kind of percentage that makes the word pilot feel entirely appropriate. We are not looking at Euclid's final dark matter map. We are watching researchers prove that the technique works with the telescope's real data. The background galaxies are measurable. Their shapes are precise enough. Independent analysis methods agree. The weak lensing pattern appears. The resulting mass reconstruction makes physical sense. That is the important milestone. Because once you can do it in one small field, the question becomes what happens when the survey covers thousands upon thousands of square degrees. And there is another useful distinction. The lensing around Abell 2390 is dominated by a huge, obvious concentration of mass. There is a galaxy cluster there. You can see the cluster galaxies. Then weak lensing reveals the much larger invisible mass distribution associated with the structure. Cosmic shear takes the idea further. There does not need to be one giant cluster in the middle of the picture. The accumulated weak lensing signal across broad fields can trace the network of matter itself. Dark matter halos, filaments, dense intersections, less dense regions, the large-scale structure that ordinary galaxy surveys only partly reveal. This is why scientists sometimes describe gravitational lensing as weighing the universe. A scale does not need to know whether the thing placed on it is shiny. It responds to mass. Lensing works differently, of course, but the useful feature is similar. A dark matter halo cannot hide from its own gravity. It can refuse to emit light. It can pass through ordinary matter with very little interaction. It can avoid every camera humans build, but if it has mass, it alters space-time, and if light crosses that altered geometry, the effect can be measured. There is something almost unfair about that. Dark matter has apparently spent the history of the universe avoiding direct photographs, and physicists responded by using the rest of the universe as a background grid. Every distant galaxy becomes a reference point. Every tiny distortion becomes evidence. Put enough evidence together, and invisibility stops being much of a hiding place. Of course, there are limits. Lensing tells us where gravitational mass is distributed. It does not automatically tell us what particle dark matter consists of. Two different dark matter theories might produce similar large-scale lensing maps. Researchers need very precise observations, smaller-scale structures, cluster collisions, galaxy behavior, laboratory experiments, and other tests to distinguish between possible models. Nor does every dark matter map have perfect resolution. Weak lensing is statistical. Where background galaxies are sparse, the reconstruction becomes less precise. Noise can create apparent features. Line-of-sight structures can overlap. Different mass distributions can sometimes produce similar lensing effects, unless additional information is available. This is why scientists do not look at one coloured mass map and announce that every blob represents a newly discovered dark matter object. The analysis comes with uncertainties. Those uncertainties are measured. Simulations are used. Alternative reconstructions are compared. Independent observations help confirm features. And as Euclid gathers more data, the statistical power grows. The same basic physical effect that once moved the apparent position of stars near the eclipsed sun now lets us study an invisible network spread across billions of light years. Strong lensing shows us the dramatic cases. Weak lensing provides the enormous statistical sample. Distance measurements add depth. Repeated observations and huge galaxy populations improve precision. And from all of that, researchers can begin constructing maps of something no telescope sees directly, which means the next place to look is not a theoretical example anymore. It is the actual cluster where Euclid has already demonstrated the method. Abell 239. O is a good place to see what happens when the simple idea of gravitational lensing meets a real galaxy cluster. From a distance, the cluster looks crowded. There are bright elliptical galaxies near the centre, thousands of fainter galaxies spread through the field, foreground stars from our own Milky Way, and tiny points of light that are actually entire galaxies far beyond the cluster. Then you notice the arcs. Some are thin, some are curved, some look like pieces of a circle that someone forgot to finish. They are not unusual galaxies shaped like bananas. They are ordinary distant galaxies whose images have been stretched by gravity. And under even more precise conditions, gravity can do something neater. It can turn a galaxy into a ring. An Einstein ring forms when a distant source, a massive foreground object, and the observer happened to line up very closely. The background source provides the light. The foreground object provides the gravity. The telescope receives the result. Because the foreground mass bends light passing around different sides of it, light from the same distant source can arrive along several paths. When the alignment is especially close to perfect and the mass distribution is suitable, those distorted images can join into a circle or something close to one. The background galaxy has not physically wrapped itself around the foreground galaxy. It is still sitting far behind it. What changed is the route taken by its light. Imagine placing a drinking glass over a pattern on a table. Move the glass around and the pattern appears distorted. Parts may stretch, parts may duplicate. A circle may become an arc. The glass is changing the path of light before it reaches your eyes. A gravitational lens does not use glass, and the physics is completely different, but the observational effect gives us the same useful idea. Something between us and the source has altered what we see. The more interesting difference is that a gravitational lens can magnify the background object. That is why astronomers sometimes call these systems nature's telescopes. A massive galaxy or cluster can increase the apparent brightness and size of a galaxy sitting much farther away. Objects that might otherwise be difficult or impossible to study become accessible because another object has accidentally provided some additional magnification. The universe did not build these lenses for astronomers. It simply failed to object when astronomers started using them. Euclid has already found a particularly striking example. During the telescope's early testing observations in September 2023, before the main survey had properly begun, Euclid archive scientist Bruno Altieri noticed something unusual around a galaxy called NGC 6505. At first, the image was not even ideal. The spacecraft was still being commissioned, and some of the early observations were deliberately out of focus, while engineers tested the telescope. Still, there appeared to be something around the centre of the galaxy. Euclid returned to the area. With better observations, the strange feature became obvious. A bright ring surrounded the centre of NGC 6505. The foreground galaxy lies about 590 million light-years away. Behind it is another galaxy roughly 4.4 billion light-years from us. The two happen to line up so closely from Euclid's point of view that the mass of NGC 6505 bends and magnifies the background galaxy's light into a nearly complete Einstein ring. NGC 6505 itself was already known. The ring was not. It had been sitting there, available to the right instrument, while previous observations had missed it. There is something useful about that discovery because it shows why resolution and survey size matter together. A rare lensing system can be scientifically interesting, but first you have to find it. If a telescope observes only tiny patches of sky, it may study each patch beautifully while missing many rare alignments elsewhere. If it scans enormous areas without enough resolution, the systems may be present in the images but difficult to recognize. Euclid was designed to combine a wide view with sharp, space-based imaging. That means it can search for unusual lenses while collecting the much larger statistical dataset needed for its main cosmology work. And the NGC 6505 ring is only one example. Euclid's early deep-field observations have already produced hundreds of strong lens candidates. Researchers used artificial intelligence to search the images. Citizen scientists inspected candidates, experts checked them, and detailed modelling narrowed the list. Many were previously unknown. Some show arcs. Some contain multiple images of distant galaxies. A small number approach the pleasing circular arrangement we call an Einstein ring. By the end of the mission, scientists expect Euclid to increase the known population of galaxy-scale strong gravitational lenses enormously. That matters because each lens is more than an attractive photograph. The exact shape of an Einstein ring depends on the gravitational field between the source and us. Change the mass of the foreground galaxy, and the ring changes. Change how that mass is distributed, and the ring changes. Add a dark matter halo around the galaxy and its gravity contributes to the lens. Add smaller concentrations of mass inside the halo and they can create additional effects. Strong lensing therefore gives researchers a way to measure mass with very high precision in the regions where the lensing is strongest. You can think of the ring as a gravitational outline. The invisible mass does not draw itself. The background light draws the consequences of its presence. This becomes especially powerful with galaxy clusters. A single galaxy can create a ring or several distorted images. A massive cluster can create an entire field of lensing features. Background galaxies appear as long arcs. Some are duplicated, others are magnified dramatically. The arrangement can become complicated enough that astronomers have to identify which arcs belong to the same original galaxy. One patch of light may be one image, another patch on the opposite side of the cluster may be another image of exactly the same object. Without lensing, those two patches would never appear separately. The foreground gravity has created multiple paths for the light to reach us. Able 239 provides exactly this kind of environment. It lies at a redshift of about 0.23, meaning its light has been travelling to us for billions of years. It is extremely massive. Euclid's 2024 image of the field revealed more than 50,000 galaxies, many at distances far beyond the cluster. Near the central region, strong lensing is easy to spot. One especially prominent feature is a giant arc produced by a more distant galaxy. Other arcs and repeated images appear around the cluster. These visible distortions already tell researchers that a tremendous amount of mass is concentrated there. But strong lensing mainly gives its most detailed information near the dense central region of a cluster. Farther outward, the obvious arcs become less common. Gravity is still affecting the light. The effect simply becomes weaker. That brings us back to the small distortions we followed earlier. Strong lensing gives researchers detailed information near the cluster center. Weak lensing extends the measurement outward over much larger distances. Combine them, and you can begin tracing the cluster from its crowded core into regions well beyond the bright central galaxies. That combination is one of the reasons Abell 2390 became such an important test for Euclid. Researchers used the telescope's early release observations to analyse the cluster in several complementary ways. Near the centre, they could use strong lensing features. Farther out, they could measure the statistical distortion of background galaxy shapes. Instead of choosing between strong and weak lensing, they joined the two. Strong lensing works best where gravity produces dramatic distortions. Weak lensing takes over where the effect becomes subtle. Together, the measurements can trace the cluster's mass profile across an enormous range of distances. In the 2026 analysis of Abell 239, researchers constrained the mass distribution from roughly 30 kiloparsecs from the centre out to about 2,000 kiloparsecs. That outer distance is around 2 megaparsecs. 1 parsec is about 3.26 light years, so 2 megaparsecs works out to more than 6 million light years. That means the lensing analysis does not simply weigh the bright centre of the cluster, it follows its gravitational structure across millions of light years. For scale, the Milky Way's bright stellar disk is roughly 100,000 light years across. The region being studied around Abell 2390 reaches enormously farther than that. Galaxy clusters are not merely piles of galaxies sitting close together. They are immense gravitational systems. Most of their mass is not contained in the visible stars of their member galaxies. A large fraction is dark matter. There is also hot gas between the galaxies, which can be detected at X-ray wavelengths. The galaxies themselves contribute mass, but when all the visible components are counted, they are not enough to explain the lensing signal. The cluster requires a much larger underlying mass distribution. That is the invisible structure Euclid is beginning to map for Abell 2390. The combined strong and weak lensing analysis produced a total mass estimate within the commonly used radius known as R200 of roughly 1.5 quadrillion times the mass of the Sun. That is one followed by 15 solar masses. it is difficult to attach an intuitive image to that number. The Sun is already about 333,000 times the mass of Earth. Now imagine 1.5 quadrillion suns. At that point, visualization begins to become less helpful, and the brain quietly goes out for tea. The important point is not simply that Abell 2390 is massive. Galaxy clusters were already known to be massive. What Euclid demonstrated is that its combination of wide field, sharp imaging, and enormous population of background galaxies can measure how that mass is distributed from the inner cluster outward. The weak lensing analysis used 3 independent methods to measure galaxy shapes. That is worth mentioning because this kind of result depends on detecting tiny effects. If only one analysis method found the signal, researchers would immediately want to know whether the algorithm itself had introduced some bias. Instead, the independent shape measurements gave consistent results. The researchers also used information from Euclid and ground-based observations to estimate the distances of background galaxies. That matters because a galaxy in front of Abell 2390 cannot be lensed by the cluster. A galaxy inside the cluster is not a useful background source either. The cleanest weak lensing signal comes from galaxies lying behind it, so the researchers had to separate the populations. They estimated redshifts, they corrected for contamination from cluster members, they considered how magnification changes the apparent population of background galaxies. They accounted for objects hiding other objects in crowded areas. None of this appears in the final image. You see a mass map. Behind that map is a great deal of work preventing ordinary observational complications from becoming imaginary dark matter. This is one reason a dark matter map should not be thought of as a direct photograph. Euclid begins with images of galaxies. Researchers measure shapes. They estimate distances. They determine how the background galaxies have been statistically distorted. Then they use those distortions to reconstruct the gravitational mass responsible for them. When the result is displayed, the inferred mass may be shown as a coloured region laid over the original image. In the Euclid visualization of Abell 2390, the reconstructed mass distribution has been shown in violet. The violet is not dark matter light. Dark matter has not changed its mind and started glowing helpfully in a colour that looks good on a press release. The colour is a way of showing where the lensing analysis says the mass is concentrated. That distinction is important because the result is actually more impressive once you understand it. Anyone can photograph something that produces light. The challenge here is to measure something that does not. The telescope never receives a photon from the dark matter itself. It receives photons from galaxies behind the dark matter. Those photons arrive slightly redistributed. From that change, researchers infer the hidden mass. In the original Euclid image, the cluster is already visually impressive. Thousands of galaxies fill the field. Bright foreground stars display the familiar diffraction spikes created by the telescope. The central cluster galaxies stand out. Lensing arcs curve through the scene. There is also faint intracluster light produced by stars that are no longer bound to individual galaxies. These stars have been stripped from galaxies during gravitational interactions and now drift through the cluster. Intracluster light is useful because it can also provide clues about how the cluster formed and where its matter is distributed. But even after accounting for all of that visible material, most of the cluster's mass remains invisible. Overlay the lensing reconstruction, and the scale of the hidden component becomes easier to appreciate. The mass is not restricted to the glowing centers of galaxies. It spreads through the cluster. It extends outward. It forms the gravitational environment in which the galaxies move. This is the difference between looking at a city at night and looking at a map of the land underneath it. The city lights show where activity is concentrated. The terrain tells you why roads and buildings may have developed in particular places. With galaxy clusters, visible galaxies show where some ordinary matter has gathered. Dark matter provides much of the gravitational terrain, and Abell 2390 is not a perfectly isolated sphere sitting alone in empty space. Galaxy clusters are connected to larger structure. Matter continues outside the conventional boundary used to define the cluster. There may be surrounding groups, Filaments can feed material toward the cluster. Smaller halos lie nearby. The wide field becomes important because it allows researchers to trace the lensing signal farther from the center than a narrow image could. This is one of the places where Euclid's design begins to show its purpose very clearly. Hubble can produce exceptionally detailed views of cluster cores. It has transformed gravitational lensing science, but its field of view is small. Euclid sees a much wider region in one observation. For the Abel 2390 work, that allowed the researchers to follow the mass profile from the strongly lensed inner area to distances around and even beyond the cluster's virial region. A virial radius is not a physical wall. There is no sign in space saying, Abel 2390 ends here. It is a useful boundary astronomers define using the average density inside a certain radius. Matter continues beyond it. The gravitational environment continues beyond it. For a mission trying to understand large-scale structure, that outer material matters. Dark matter halos do not exist independently of the cosmic web. They grow within it. They merge. They accrete smaller structures. Clusters form where large flows of matter come together. So measuring only the bright center tells you part of the story. Measuring the outskirts helps connect the cluster to the universe around it. The combined lensing profile of Abel 2390 was well described by a commonly used dark matter halo model called a Navarro-Frank-White profile, usually shortened to NFW. The name comes from Julio Navarro, Carlos Frank and Simon White, who found through cosmological simulations that dark matter halos tend to develop a characteristic density structure. The density is higher toward the center and falls with distance, though not in the same way at every radius. Astronomers have used this profile for decades to compare observed galaxies and clusters with predictions from simulations of cold dark matter. Abel 2390's lensing data were consistent with this kind of profile across the wide radial range studied. That does not mean the mystery of dark matter has been solved. It means the observed gravitational structure of this cluster fits an important expectation of the standard dark matter picture. And that is exactly the kind of test Euclid can repeat. One cluster is useful. A few clusters are better. Thousands begin to become cosmology. This is where the phrase, Euclid's first map of the invisible, needs a little care. Astronomers were mapping dark matter with gravitational lensing long before Euclid launched. Hubble produced famous dark matter maps. Ground-based surveys measured weak lensing across huge sky areas. Abel 2390 itself had been studied before. Euclid did not invent dark matter mapping. What the 2026 work provided was the first demonstration using Euclid data of the mission's planned weak lensing capability to reconstruct a mass distribution dominated by dark matter with this kind of precision and wide coverage. In other words, this was not humanity's first dark matter map. It was Euclid showing that it can do the job it was built to do. That may sound less dramatic than saying the telescope suddenly found the hiding place of all dark matter. Scientifically, it is more important. A one-time spectacular discovery can teach us about one object. A measurement technique that works reliably can be applied again and again. Abel 2390 is valuable because it is a demonstration. The method works on real Euclid observations. The telescope's image quality is good enough. The background galaxies are plentiful enough. Their tiny distortions can be measured. Different analysis methods agree. Strong and weak lensing complement one another. The mass profile can be followed across millions of light years. Now consider how small this field is compared with Euclid's planned survey. The weak lensing pilot observation around Abel 2390 represents less than 0.004% of the sky area Euclid intends to cover, less than 0.004%. If that sounds almost comically small, it should. Imagine opening an atlas, placing the tip of a pencil on one tiny patch, and being told that the final project involves mapping a continent. Abel 2390 shows what can be extracted from the pencil mark. The wider survey is the continent. Across that survey, Euclid will observe galaxies in enormous numbers. Some foreground galaxies will create strong lenses. A few will produce nearly complete Einstein rings. Massive clusters will stretch distant objects into arcs. Weak lensing will subtly alter the shapes of background galaxies across almost every field. Those individual distortions will be small, but the accumulated data will allow researchers to build statistical maps of matter across large sections of the universe. That is when dark matter halos begin to matter beyond the individual cluster. Every large galaxy is expected to sit inside one. Groups have larger shared halos. Clusters have enormous halos. Smaller concentrations of dark matter can exist within larger ones. And the halos themselves are connected by filaments forming the cosmic web. An Einstein ring gives us a particularly clean reminder that a galaxy is gravitationally larger than the bright object we see. The stars in the foreground lens contribute to the bending. But the dark matter halo surrounding the galaxy contributes as well. Measure the lens carefully enough, and you can constrain the total mass distribution, including the part extending beyond the bright stars. With thousands of strong lenses, researchers can begin asking whether halos around galaxies have the structures predicted by dark matter models. With weak lensing around enormous populations of galaxies, they can measure the average halo properties statistically. Around clusters, they can trace much larger distributions. Across the wider sky, they can follow how those concentrations connect. The method changes scale without changing the basic clue. Light comes from behind. Gravity alters its path. Euclid measures the result. A bright ring around NGC6505 is the version you can see immediately. A giant arc in Abel 2390 is another. The tiny average stretch of thousands of background galaxies is harder to notice, but it contains the information needed to map much more of the invisible mass. When we look at a photograph of the Milky Way's nearest large neighbours, or at a spiral galaxy hundreds of millions of light years away, our attention naturally goes to the bright part. That seems reasonable. The bright part is, after all, the part that bothered to appear in the photograph. We see a glowing centre, a disk, spiral arms, dark lanes of dust, scattered regions where new stars are forming, perhaps a faint outer glow. Then the light fades into the background and the galaxy appears to end. Gravitationally it does not. The visible stars occupy only part of a much larger structure. Surrounding the galaxy is a halo of dark matter. The word halo can create the wrong picture if you imagine a neat glowing ring floating around the outside. A dark matter halo does not begin where the stars stop, and it does not sit around a galaxy like packaging. The stars are inside it, the gas is inside it, the central black hole is inside it. The visible galaxy occupies the deeper central region of a much larger distribution of mass. And unlike the disk of a spiral galaxy, which is relatively flat, the dark matter halo is expected to be much more extended in 3 dimensions. Depending on the galaxy and the details of its history, the halo may be roughly spherical, somewhat flattened, stretched in one direction, disturbed by mergers, or filled with smaller concentrations that once belonged to smaller systems. So when we ask where dark matter gathers, one major answer is around galaxies, not only between them, not only inside giant clusters, around individual galaxies, forming gravitational structures much larger than the light suggests. We encountered the first major clue earlier when we looked at galaxy rotation. Stars and gas in the outer regions of spiral galaxies move too quickly to be explained by the visible matter alone. If most of the mass were concentrated where most of the starlight is, orbital speed should fall much more noticeably as we move outward. Instead, rotation curves often remain roughly flat across regions where the visible light is becoming much fainter. That is telling us something about the mass. There must be additional matter extending outward. A lot of it. Imagine a city whose streetlights become sparse toward the suburbs. From the lights alone, you might conclude that the city is ending. then you discover that traffic is still moving through a much larger road network in complete darkness. The roads did not stop where the lamps stopped. You were simply using the wrong thing to define the edge. The same problem appears with galaxies. Starlight is not a reliable boundary marker for the gravitational system. Our own Milky Way is a good example. Its familiar stellar disk stretches roughly 100,000 light-years across, depending on exactly how you define the outer regions. But the Milky Way's dark matter halo extends much farther. Astronomers estimate the galaxy's total mass by studying the motions of stars, satellite galaxies, globular clusters, and other objects moving through its gravitational field. Different techniques produce somewhat different estimates, which is hardly surprising when you're trying to weigh an invisible structure while sitting inside it. Still, the overall conclusion is clear. Most of the Milky Way's mass is not in the stars we see. The galaxy is embedded in a vastly larger halo. That also means the solar system is inside dark matter right now. Not in the sense that dark matter is collecting on the desk or quietly hiding behind the curtains. The density near the sun is thought to be extremely low by everyday standards. Dark matter particles, whatever they are, may be passing through Earth continuously without producing noticeable interactions. The point is that our location inside the visible disk also places us inside the Milky Way's much larger gravitational halo. We do not live next to dark matter. We live within a structure dominated in mass by it. That makes the challenge slightly amusing. Humanity has spent decades building experiments to search for a substance that may already be passing through the laboratory. It is simply refusing to introduce itself. The halo itself does not have a perfectly sharp edge. Astronomers often use practical definitions when discussing halo sizes. One common approach is to define a radius inside, which the average density is some specified multiple of the critical density of the universe. You may see terms such as R200 or virial radius. These are useful boundaries for comparing galaxies and simulations. They are not walls. A dark matter particle does not reach R200, look at a sign and turn around. Matter extends beyond those formal boundaries. Neighbouring halos interact. Material falls inward. Satellite galaxies move through the outer regions. Large-scale filaments connect one system to another. The edges become increasingly difficult to define because galaxies are part of the cosmic web rather than isolated islands floating in emptiness. Inside the halo, the density of dark matter is generally expected to increase toward the centre. One widely used description is the Navarro-Frank-White profile, the same general kind of profile we mentioned when looking at Abell 2390. Computer simulations of cold dark matter showed that halos produced through cosmic structure formation often develop a characteristic distribution. The density is relatively high toward the inner region and falls outward. That basic picture has been remarkably useful. But real galaxies contain ordinary matter too, and ordinary matter complicates things. Gas can cool, stars form, supernovae inject energy, black holes release enormous amounts of energy into surrounding material, galaxies merge, gas flows inward and outward. All of this can affect the gravitational environment and potentially change the central distribution of dark matter. So a real dark matter halo is not simply a featureless theoretical ball sitting around a decorative collection of stars. The visible galaxy and the dark halo have developed together. That relationship is one of the reasons measuring halo shapes and density profiles matters. Different dark matter models can produce different small-scale structures. Ordinary matter can modify those structures. If researchers want to use halo measurements to learn what dark matter is, they have to separate the effects of dark matter physics from several billion years of galaxies behaving like galaxies, which, unfortunately, they have done with great enthusiasm. Stars explode, gas moves, black holes feed, galaxies collide, satellite galaxies are torn apart. Nothing simply sits still and waits to be measured. One particularly useful consequence of that chaos is the formation of stellar streams. A stellar stream is a long, thin trail of stars created when gravity pulls apart a smaller object such as a globular cluster or dwarf galaxy. Imagine a small satellite galaxy orbiting a much larger one. The larger galaxy's gravity is not exactly the same across the satellite. The side closer to the host feels a slightly different gravitational pull from the side farther away. Over time, stars can be stripped from the satellite. Instead of immediately scattering randomly into space, many remain on related orbits. They stretch out into a long stream. Some streams wrap around their host galaxy. Others form arcs, loops, or extended faint structures. They can persist for billions of years, and because their paths respond to gravity, they become useful tracers of the host galaxy's gravitational potential. This is a different way to investigate a halo. Weak gravitational lensing uses light from background galaxies. Stellar streams use stars moving inside the gravitational environment itself. Think of placing a floating ribbon in moving water. The shape of the ribbon gives you clues about the current. You may not see the water moving in detail, but the ribbon responds to it. A stellar stream does something comparable in a galaxy's gravitational field. Its path depends on the distribution of mass. If the halo were strongly flattened in one direction, the stream would respond differently than it would inside a spherical halo. If the center of mass were shifted, the orbit could change. If smaller dark matter clumps pass nearby, they might disturb the stream, creating gaps or other features. The stars are providing a record of the gravity they have experienced. The Milky Way has several known stellar streams, and because we're inside our galaxy, astronomers can sometimes measure the positions and motions of individual stream stars with extraordinary precision. That has turned streams into important probes of the Milky Way's dark matter halo. External galaxies are harder. From millions of light years away, individual stars in a faint stream may be difficult or impossible to resolve. The stream may appear only as a very faint extended feature around the brighter host galaxy. Finding large numbers of them therefore requires deep, sharp imaging over broad areas. Which is another description that sounds suspiciously like Euclid, and by 2026 Euclid data had already begun being used for exactly this kind of work. Researchers studying Euclid's first quick data release identified galaxies with prominent tidal streams and used the shapes of those streams to constrain the geometry of their host galaxy's gravitational potentials. This is important because the gravitational potential includes both ordinary matter and dark matter. The stars in the main galaxy contribute, gas contributes, dark matter contributes, but far from the brightest central regions, the extended dark matter halo becomes increasingly important. The Euclid study examined 13 galaxies with prominent stellar streams. 13 is not an enormous cosmological sample. Nobody is going to reorganize the entire theory of dark matter based on 13 galaxies. But the point was to demonstrate what becomes possible when Euclid's wide survey begins finding these delicate structures in large numbers. The early results were consistent with roughly spherical halos, with a mild preference for slight flattening. That is broadly compatible with expectations from the standard cold dark matter picture. More importantly, the method can scale. Euclid's first quick release area covered only around 60 square degrees. The main survey is designed to cover roughly 14,000 square degrees. If the small early sample is any indication, the full survey could contain thousands of useful stellar streams, potentially many thousands. Suddenly, a technique that once worked mainly for our own galaxy and a handful of nearby systems becomes something that could be applied statistically across a much larger population. That changes the question. Instead of asking, what shape is the Milky Way's dark matter halo? We can begin asking, what shapes do dark matter halos usually have? Do small galaxies live inside halos shaped differently from massive galaxies? Are halos generally spherical, flattened, elongated? Does the shape change depending on the galaxy's environment? Does a galaxy sitting in a crowded group have a different halo from an isolated galaxy? How well is the dark matter centered on the visible galaxy? Do halo shapes change across cosmic time? And do those measurements agree with simulations built using cold dark matter? Those questions matter because different dark matter properties can influence halo structure. Cold dark matter models predict a hierarchy of halos. Small halos form, they merge into larger halos, those merge again. The process continues. A large galaxy's halo is therefore not necessarily a smooth object created all at once. It has a history. Smaller halos fall into it. Some survive as subhalos. Some contain visible satellite galaxies. Others may contain so little ordinary matter that they remain almost completely dark. This leads to an important point. A dark matter halo does not always need a bright galaxy at its centre. The relationship between galaxies and halos is not one galaxy equals one obvious dark blob. Large galaxies sit in large halos. Satellite galaxies can occupy smaller subhalos within those halos. Some predicted subhalos may contain very few stars. At the smallest scales, some may contain none that we can detect. That makes them extremely difficult to find. A dark subhalo without stars is essentially a gravitational structure, with no visible sign announcing its location. Again, lensing becomes useful. If a small dark matter concentration lies near the line of sight to a strongly lensed background object, its gravity can slightly alter the lensing pattern. Researchers can search for these deviations. Hubble observations have already detected small dark matter clumps through gravitational lensing, even when those concentrations contained no visible stars. That is a remarkable idea. A structure too dark to photograph can still interfere with the image of something behind it. The background source becomes a probe. The foreground dark matter gives itself away by changing the probe. Euclid's large population of strong gravitational lenses can eventually make this kind of investigation more statistical. Remember the scale we discussed earlier. Euclid's early deep field release produced hundreds of galaxy-scale strong lens candidates, almost all previously unknown. The mission is expected to find vastly more as the survey expands. Every strong lens includes a foreground galaxy and its surrounding mass. That foreground mass includes the dark matter halo, so each system can provide information about how matter is distributed around galaxies. Not every lens will be suitable for detailed dark matter substructure studies. Some alignments are more useful than others. Image quality matters. The background source matters. The lens geometry matters. But large samples change the odds. Rare useful systems stop being quite so rare when you inspect enough sky. Weak lensing provides another route to galaxy halos. Instead of analysing the dramatic arcs around individual galaxies, researchers can measure the tiny average distortion of background galaxies around large samples of foreground galaxies. This is called galaxy-galaxy lensing. Take many foreground galaxies that share some property. Perhaps they have similar stellar masses. Perhaps they are similar colours. Perhaps they live in similar environments. Now measure the shapes of more distant galaxies behind them. The lensing signal from one foreground galaxy may be too weak to measure clearly. Stack thousands or millions together and an average pattern appears. The average tells researchers about the typical mass distribution around the foreground population. In other words, you can weigh an average galaxy without seeing most of its mass. Change the sample and repeat. How does halo mass relate to the number of stars? Do red galaxies sit in different halos from blue galaxies? How does halo structure depend on environment? What happens to satellite galaxies when they move through larger halos? How much dark matter is stripped from them? Euclid's enormous survey makes these statistical questions particularly powerful because it will observe huge numbers of foreground and background galaxies across different distances. This is where the phrase, "where dark matter really gathers," becomes more interesting than simply saying, "around galaxies." Dark matter does gather around galaxies, but the amount and arrangement are not the same everywhere. A small dwarf galaxy may inhabit a halo whose dark matter mass is enormous compared with the mass in its visible stars. A large spiral galaxy may have a much more massive halo containing a bright stellar disk. A giant elliptical galaxy near the center of a group may sit inside a halo that blends into a much larger group environment. A central galaxy in a cluster may occupy the deepest region of an enormous cluster-scale halo shared by hundreds or thousands of galaxies. Satellite galaxies live inside that larger structure while retaining some portion of their own smaller halos. Then beyond those halos lie filaments connecting groups and clusters across millions of light years. So there is a hierarchy. Subhalos inside halos, halos inside groups, groups feeding clusters, clusters connected by filaments. The visible galaxies are markers embedded throughout this structure. It is less like a set of marbles scattered through space and more like lights attached to an enormous gravitational framework. One reason cosmologists care about the halo-galaxy connection is that dark matter alone does not tell us where stars should form. A simulation can predict a population of dark matter halos. Astronomers observe a population of galaxies. Connecting the two is a major part of modern cosmology. How massive does a halo need to become before it efficiently forms stars? Why are some halos filled with bright galaxies while others remain faint? How does star formation change as a galaxy's halo grows? What happens when a galaxy falls into a cluster? Does its dark matter halo get stripped before its stars are disturbed? These questions connect invisible structure with visible evolution. Consider a satellite galaxy entering a larger halo. It begins experiencing tidal forces. Its outer dark matter can be stripped away. Gas may also be removed through interactions with the surrounding environment. The satellite's ability to form new stars may decline. Eventually, its orbit may bring it close enough to the central galaxy for a merger. The dark matter halos interact throughout this process, so even though we cannot photograph the halos, they influence the lives of galaxies. They affect where galaxies form, how they move, how they merge, how satellites survive, where gas collects, and indirectly, where stars appear. The visible universe grows inside an invisible gravitational architecture, but the architecture is not perfectly rigid. Ordinary matter can also influence dark matter. As gas cools and falls toward a galaxy's center, the gravitational potential changes. Dark matter can respond. Repeated bursts of star formation and energetic feedback can move gas around, especially in smaller galaxies. That can alter the central gravitational field. Over long periods, this may change how dark matter is distributed in the inner halo. This is part of a long-running question about dark matter density near galaxy centers. Simple cold dark matter simulations without detailed ordinary matter physics often produce halos whose central density rises steeply. Observations of some galaxies appear to favor flatter central distributions. Whether that difference is caused by the behavior of ordinary matter, properties of dark matter itself, observational complications, or some combination remains an active area of research. The distinction is important because the center of a halo is one of the places where competing models may differ. On larger scales, many models can look similar. Zoom in and the details may become more revealing. How many small subhalos exist? How dense are they? What shapes do halos have? How strongly does dark matter interact with itself? Does it behave exactly like a cold, nearly collisionless particle population? Every measurement narrows the possibilities. This is why Euclid's value is not only that it can create one enormous dark matter map, it can approach halos in several different ways. Weak lensing measures mass statistically around galaxies and clusters. Strong lensing can examine dense central regions and detect smaller gravitational disturbances. Stellar streams trace the gravitational potential through their shapes. Galaxy clustering reveals how halos are distributed through large-scale structure. Observations across different redshifts show how those structures change with time. Each method has different uncertainties. That is useful. When several methods agree, the result becomes harder to dismiss as a quirk of one technique. The early Euclid stellar stream result from 2026 is particularly interesting in that sense. Those researchers were not using background galaxies distorted by gravitational lensing. They were using the shapes of tidal debris around the galaxies themselves. The streams follow the host gravitational potential. The geometry of the stream therefore carries information about the geometry of the halo. 13 early systems suggested halos consistent with being close to spherical, though the constraints still allowed some flattening. The sample is too small for sweeping conclusions. The full survey is the important part. If Euclid finds thousands of suitable streams, researchers can compare halo shapes across a much broader population. And then something that has traditionally been difficult becomes statistical. Maybe halos of a certain mass are slightly more elongated. Maybe isolated halos differ from those in groups. Maybe the alignment between the dark halo and the visible stellar disk changes with galaxy type. Maybe the centers do not always line up exactly. Or perhaps the large sample will closely match the predictions of the standard model. A null surprise is still a scientific result. Sometimes the universe behaves exactly as expected, which is mildly inconsiderate when everyone has prepared a dramatic presentation. The point is that Euclid can ask these questions across enough galaxies for the answers to become meaningful. And while dark matter halos may sound like objects surrounding galaxies one at a time, they do not remain separate indefinitely. Gravity keeps building larger structures. Small halos merge. Larger halos draw in more material. Groups develop. Clusters grow. At the same time, not all matter ends up inside a neat halo centered on a visible galaxy. Follow the halos outward, through groups and clusters, and eventually they connect into the cosmic web. This is where the scale becomes difficult to hold in your head. A dark matter halo around one galaxy may stretch for hundreds of thousands of light years. A galaxy cluster can occupy a region millions of light years across. But the structures connecting clusters can extend for tens or even hundreds of millions of light years. At that scale, individual galaxies begin to look less like separate objects and more like markers. They show us where the underlying structure is. Take a map containing millions of galaxies and gradually zoom out. At first, you notice pairs and small groups. Zoom farther and the groups gather into clusters. Farther again, the clusters do not appear randomly scattered. They sit along extended structures. Some look like threads. Some resemble flattened walls. Where several structures meet, enormous galaxy clusters form. Between them lie regions containing far fewer galaxies. These quieter regions are called cosmic voids. Put everything together and the pattern begins to resemble a web, hence the name, the cosmic web. It is one of those scientific terms that is unusually helpful, because the thing really does look rather web-like. Not a perfectly organised spider web with a patient spider sitting politely in the centre. More like a tangled three-dimensional network built from filaments, knots, sheets, and large empty-looking spaces. And the galaxies we see are only part of it. Most of the matter shaping that network is dark matter. That is why the cosmic web can be thought of as the large-scale gravitational skeleton of the universe. The phrase does not mean dark matter forms rigid cosmic bones. Nothing is fixed in place. Matter moves. Galaxies fall toward denser regions. Clusters grow. Filaments evolve. Voids expand. The entire structure changes as the universe ages. The skeleton comparison is useful because dark matter provides much of the framework along which ordinary matter gathers. Stars illuminate parts of the structure. Galaxies make sections of it visible. Hot gas occupies other parts. But dark matter dominates the mass. To understand how something this large could form, we have to go back to a time when the universe looked much smoother than it does now. The early universe was hot and dense. Matter and radiation filled space much more uniformly. There were no mature galaxies, no giant galaxy clusters, no familiar spiral arms, no enormous cosmic web spread across billions of light years. But the early universe was not perfectly uniform. There were tiny variations in density. Some regions contained slightly more matter than others, very slightly. The differences were small enough that describing one region as a crowded neighbourhood and another as an empty suburb would be wildly generous. They were tiny fluctuations. Gravity, however, is very patient. A region containing slightly more matter has slightly stronger gravitational attraction. That attracts additional matter. Now the region contains a little more mass. Its gravitational pull grows. More matter moves toward it. Over millions and then billions of years, tiny differences become large ones. Dense regions grow denser. Less dense regions lose material to their surroundings. The original small fluctuations become galaxies, clusters, filaments, and voids. Dark matter plays a central role because it does not interact with radiation the same way ordinary matter did in the early universe. Ordinary matter consists largely of particles such as protons and electrons. Before the universe cooled enough for neutral atoms to form, those charged particles interacted strongly with light. Radiation and ordinary matter were tightly connected. Dark matter, as far as we can tell, did not participate in that electromagnetic interaction. Its gravity was already available, so dark matter could begin building gravitational concentrations, while ordinary matter was still dealing with the rather inconvenient fact that the early universe was full of radiation. When the universe became cool enough for electrons and nuclei to combine into neutral atoms, ordinary matter could fall more freely into the gravitational structures dark matter had been developing. Gas flowed toward denser regions. It collected inside dark matter halos. Stars formed. Galaxies followed. Then galaxies gathered into larger systems. You can think of dark matter as preparing much of the terrain before the visible structures arrived. Not completely. Ordinary matter has gravity too. And once stars and galaxies form, ordinary matter can affect the development of structures in complicated ways. But on large scales, dark matter is the dominant material component. Its distribution provides the basic framework. Computer simulations make this process easier to visualize. Researchers begin with a model of the early universe containing small density fluctuations, consistent with observations. They include gravity. They include dark matter. More detailed simulations include gas, star formation, black holes, stellar explosions, radiation, and many other pieces of physics. Then they allow the simulated universe to evolve. Dark matter particles begin collecting into small halos. Halos merge. Larger halos form. Matter flows along sheets. Sheets collapse into filaments. Filaments feed dense intersections. At those intersections, clusters grow. Meanwhile, the less dense regions become emptier as material moves away from them. By the present day, the simulated matter distribution resembles the cosmic web seen in galaxy surveys. It is one of the great successes of the modern cosmological model. Start with tiny fluctuations. Apply gravity for nearly 14 billion years. Get a universe that looks remarkably similar to ours, which makes gravity sound almost suspiciously productive. Give it enough time, and a small unevenness becomes a galaxy cluster. The web is not merely decorative structure. Its shape depends on the ingredients of the universe. Change the amount of dark matter and structure grows differently. Change the behavior of dark matter and smaller halos may form differently. Change the expansion history of the universe, and gravity has more or less opportunity to pull matter together. Change the law of gravity and the growth of the network changes again. That is why Euclid cares about the cosmic web. The web contains a record. Its structure tells us something about what the universe contains and how those ingredients behaved over time. Suppose gravity had been slightly less effective at bringing matter together. The large-scale distribution today would be smoother. Clusters might be less massive. Filaments might be less pronounced. Suppose cosmic expansion had slowed more strongly in the past. Matter would have had more opportunity to gather. If accelerated expansion became important earlier, structure growth would be suppressed sooner. The The universe we observe today is therefore one particular outcome from a long competition between gravitational attraction and cosmic expansion. Dark matter helps matter clump. Expansion separates distant regions. Dark energy is connected in our current model with the accelerated expansion that has increasingly opposed the growth of large-scale structure. Euclid was built to measure both sides of that story, the expansion history and the growth of structure. The cosmic web is where the second part becomes visible, but there is a complication. We cannot simply take a photograph of the web's dark matter. What we photograph most easily are galaxies. Fortunately, galaxies do not appear in random places. They tend to form inside dark matter halos. Those halos occupy the cosmic web, so the galaxy distribution traces the underlying matter distribution. Not perfectly. A galaxy is not a glowing dark matter particle. Different types of galaxies can trace the underlying matter in different ways. Massive galaxies may prefer denser environments. Some galaxies live near cluster centers, others occupy filaments, some lie near void boundaries. This relationship between visible galaxies and underlying matter is called galaxy bias. It means that a galaxy map is related to the dark matter map, but it is not identical to it. Researchers need models describing that relationship. Then they can use the galaxies as tracers. Euclid approaches the web from more than one direction. One method uses weak gravitational lensing. We have already followed that idea from individual galaxies to Abel 2390. Light from distant galaxies travels through the uneven matter distribution between the source and Euclid. Dark matter halos bend it. Clusters bend it. Filaments contribute. Other concentrations along the line of sight contribute too. Measure enough background galaxy shapes, and researchers can reconstruct the projected distribution of matter. That includes the dark component. The other major method uses galaxy clustering. Here, Euclid does care very much about where galaxies are. Not only their direction on the sky, their distance as well. A two-dimensional image might show two galaxies next to one another, even though one is billions of light years farther away. To reconstruct the cosmic web properly, astronomers need the third dimension. Euclid obtains precise spectroscopic redshifts for tens of millions of galaxies. A redshift tells researchers how much a galaxy's light has been stretched as the universe expanded during its journey toward us. From that information, along with the cosmological model, astronomers can determine where galaxies sit along the line of sight. Now the flat picture gains depth. A point on the sky becomes a position in three-dimensional cosmic space. Do that around 35 million times and the points begin forming a structure. Clusters appear as dense knots. Filaments connect them. Voids open between the filaments. The web emerges from the coordinates. Euclid's planned spectroscopic galaxy sample covers a period when the universe was significantly younger than it is today. The weak lensing sample reaches across an even broader range. That means Euclid is not making only one map of the web as it exists now. It can examine the distribution at different cosmic times, look farther away, and the light has travelled longer. We see those galaxies at an earlier stage in the universe's history. Nearer galaxies show us a more recent stage, so distance becomes a kind of time machine, not one that lets us visit the past. You still cannot go back and tell yourself not to send that message, but light allows us to observe different eras at once. A distant section of Euclid's survey shows an earlier universe. A nearer section shows a later one. Compare them and researchers can measure how cosmic structure developed. At earlier times, the web was less mature. The density contrasts were smaller. Clusters were still assembling. As time passed, gravity pulled more matter toward filaments and nodes. Voids became increasingly empty relative to the dense structures around them. Clusters gained mass. The network became more pronounced. This evolution is called structure growth. It is one of Euclid's main targets. And the first public Euclid survey data have already shown that the telescope can recover parts of this network. In March 2025, Euclid released its first quick data release, covering about 63 square degrees across 3 deep field regions. That represents less than 1% of the mission's planned wide survey. Even within that early area, researchers were able to identify galaxy filaments and examine how galaxies and clusters relate to the surrounding cosmic web. Think about what that means. The telescope had barely begun providing survey data, and the large-scale network was already visible in the distribution of galaxies. Not the final dark matter map. Not Euclid's full cosmological measurement. Those require far more data and much more analysis. But the structure Euclid was built to study was already appearing. Clusters sat at intersections. Galaxies traced filaments. Different environments could be compared, and these early fields covered only a small fraction of the sky Euclid will eventually examine. ESA's first data release included around 26 million galaxies detected in the three main mosaics. 26 million is already an inconvenient number of galaxies to imagine. Picture one galaxy. Perhaps something resembling the Milky Way, hundreds of billions of stars. Now imagine 26 million galaxies. The mind eventually stops producing useful images and replaces them with a vague sense that there are quite a lot. Euclid's final datasets go far beyond that. For weak lensing, the mission is designed to measure shapes for roughly 1.5 billion galaxies. For its three-dimensional clustering analysis, it is expected to obtain precise spectroscopic information for around 35 million galaxies. These are not numbers collected simply because astronomers enjoy large spreadsheets. The enormous samples are necessary because cosmology is statistical. One filament can have an unusual history. One cluster can have an unusual merger. One void can be oddly shaped. 1 billion galaxies allow researchers to move beyond individual stories. They can measure typical behavior. How common are structures of a certain size? How strongly are galaxies clustered at a given distance? How does the clustering pattern change over time? How does weak lensing correlate with galaxy positions? Do the two independent methods describe the same underlying universe? That last question is especially important. Galaxy clustering traces where luminous galaxies live. Weak lensing responds directly to the total gravitational mass along the line of sight. Compare them. If the standard cosmological model is correct, the two should fit together in predictable ways. The galaxies should inhabit the matter distribution in a way consistent with dark matter simulations. The lensing signals should correspond to the gravitational structures traced statistically by those galaxies. If they do, the model survives another test. If they do not, researchers have work to do. First, naturally, they check the instruments. Then the calibration. Then the redshifts. Then the galaxy selection method. Then the model used to connect galaxies with dark matter. Then probably several things involving very large computer clusters and coffee. Only after those possibilities have been examined does anyone begin using phrases such as new physics. Cosmology has learned to be cautious. The universe is complicated enough without accidentally discovering a revolution caused by a poorly corrected detector. Simulations are essential for exactly this reason. Before comparing Euclid with theories, researchers create synthetic universes. The Euclid Consortium has produced huge simulated galaxy catalogues, designed to resemble what the telescope should observe. One recent flagship simulation contains billions of model galaxies spread through a synthetic cosmic web. The underlying calculation contains dark matter halos. Galaxies are assigned to those halos according to models calibrated against observations. Their positions, brightnesses, velocities, shapes, and many other properties can then be compared with what Euclid actually sees. This gives scientists a controlled universe where the answer is known. That is a luxury nature does not normally provide. In the real universe, researchers observe a filament and ask how much dark matter it contains. In a simulation, they can inspect the dark matter directly because the computer knows where every simulated component was placed. Then they process the simulated observations as though Euclid had collected them. Do the analysis methods recover the correct structure? Do weak lensing algorithms reconstruct the known mass? Do galaxy clustering measurements return the cosmological parameters used to create the simulation? If not, something in the analysis needs improvement. It is essentially a rehearsal. Admittedly, a rehearsal containing billions of galaxies and enough data to make an ordinary laptop quietly reconsider its career choices. The filaments themselves are especially interesting. A filament is not simply a line of galaxies. It is an elongated concentration of matter connecting denser regions. Dark matter makes up much of the mass. Gas occupies the filament too. Galaxies and galaxy groups are embedded within it. Matter can flow along filaments toward clusters. In that sense, the cosmic web contains something resembling a transportation network. Small structures enter larger ones. Galaxies move toward groups. Groups can move toward clusters. Gas feeds galaxies and clusters. Mergers happen more frequently in certain environments. The network influences how galaxies evolve. A galaxy living deep inside a rich cluster experiences a very different environment from one sitting quietly inside a void. Cluster galaxies move through hot gas. They encounter neighbouring galaxies. Their own gas supplies may be stripped or disrupted. A galaxy inside a filament may experience different patterns of gas accretion and interactions. A galaxy near the centre of a void may evolve with far fewer close neighbours. So the cosmic web does not merely tell us where galaxies are. It helps shape what they become. Euclid's wide survey lets researchers compare galaxies across these environments. Do galaxies near filaments tend to align with the filament direction? Does star formation change as galaxies approach dense nodes? How are clusters connected to surrounding filaments? What kinds of galaxies live near void boundaries? The 2025 Euclid release already allowed researchers to explore some of these questions statistically across its early fields. As the survey expands, the sample will become far larger. Voids deserve attention too. Calling them empty can be misleading. Cosmic voids are underdense regions, not perfect vacuum bubbles. They can contain galaxies. They contain matter. They may contain faint filaments and small halos. There is simply much less matter than in the dense region surrounding them. And because they are underdense, voids respond to cosmic evolution differently from clusters. Matter tends to move away from void interiors toward denser surrounding regions. As the universe evolves, many voids grow. Their shapes and sizes therefore provide another way to study large-scale structure. The edges of voids can be traced by galaxies. Weak lensing can help probe their mass distribution. Their statistics can be compared with simulations. Once again, dark matter that cannot be seen directly influences something we can measure. The cosmic web therefore contains information at both extremes. At the knots are galaxy clusters, among the densest large structures in the universe. Between them are voids, enormous regions with relatively little matter. Filaments connect the dense areas. Sheets provide broader structures around parts of the network. The entire pattern emerged from the same early density fluctuations. What differs is how gravity amplified those fluctuations over time. There is another subtle feature hidden in galaxy clustering. Galaxies do not only reveal where matter is located, their distribution retains a statistical pattern left over from sound waves in the early universe. These are called baryon acoustic oscillations. Before atoms formed, ordinary matter and radiation behaved as a hot-coupled fluid. Pressure from radiation pushed outward while gravity pulled matter inward. That created waves. When the universe cooled enough for light to travel freely, the waves stopped propagating in the same way, leaving behind a preferred scale in the distribution of matter. Billions of years later, that scale remains detectable statistically in the distances between galaxies. It acts something like a cosmic ruler. Measure its apparent size at different redshifts, and researchers can study how the universe expanded. So Euclid's galaxy map does double duty. The overall clustering tells us about structure. A specific statistical scale inside that clustering tells us about expansion. Then there are redshift space distortions. Galaxies are carried apart by cosmic expansion, but they also move locally because gravity pulls them toward dense structures. Those additional motions slightly distort the three-dimensional clustering pattern when distances are inferred from redshifts. Instead of treating that as an annoyance, astronomers measure it. The distortions reveal how quickly matter is falling into large-scale structures. That provides another test of structure growth and gravity. Euclid is effectively using galaxies as both landmarks and moving test particles. Where are they? How are they clustered? How fast are they moving toward dense regions? How are background galaxy shapes distorted by the matter between us and them? Each question attacks the same cosmic structure from a different angle. That is how the web becomes more than a picture. It becomes an experiment. And dark matter is central to that experiment because the web's visible galaxies are only the bright markers of a much larger mass distribution. The filaments we see in galaxy maps exist because the underlying matter is concentrated there. Clusters grow at intersections because enormous dark matter halos have assembled in those locations. Voids contain fewer galaxies because they contain less matter. The whole arrangement reflects dark matter's gravitational history, which brings us back to the title of this journey. Where does dark matter really hide? Not in one secret corner, not behind one galaxy, not inside a single mysterious object. It is spread throughout the structure of the universe, around galaxies, through groups, across clusters, along filaments, around the boundaries of voids. Its distribution is not random. It forms a connected pattern spanning scales so large that light itself needs hundreds of millions of years to cross some of the structures. And because the web evolves, mapping it at different distances lets Euclid compare the invisible universe at different ages. That is the larger promise behind the small dark matter reconstruction around Abel 2390. Abel 2390 is one massive intersection. Euclid's full survey is designed to place that knot inside the wider network, then another and another. Eventually, clusters become nodes in a three-dimensional structure stretching through enormous volumes of space. Weak lensing adds the distribution of total matter. Galaxy clustering adds precise positions for tens of millions of luminous tracers. Together, the two measurements allow scientists to test whether the cosmic web grew the way our current theories say it should. Perhaps it did. Perhaps dark matter behaves almost exactly like the cold, nearly collisionless substance assumed in the standard model. Perhaps dark energy behaves like a cosmological constant. Perhaps general relativity continues working perfectly on the largest measurable scales. That would be an extraordinary result, even if it lacks the satisfying drama of discovering that Einstein forgot something on page 47. But there are other possibilities. The web may grow slightly too quickly, or too slowly. Matter may clump differently from predictions. Weak lensing and galaxy clustering may disagree in a persistent way. The abundance of clusters at certain times may prove difficult to reproduce. Void statistics may reveal unexpected behavior. The distribution of small halos may hint that dark matter has properties beyond the simplest model. Euclid does not know what answer it is looking for. That is the point. It measures. The theories have to survive the measurement. And somewhere inside that huge network, there is another possibility worth examining. Dark matter normally gives galaxies a place to form. We're accustomed to finding an invisible halo and somewhere near its center, a visible collection of stars. But nature does not have to make the relationship convenient. Some halos may form very few stars. Some galaxies may contain surprisingly little luminous material compared with their total mass. Under the right conditions, an enormous concentration of matter can become extraordinarily difficult to see, even when you know roughly where to look. Once Euclid began surveying the web with its combination of depth and wide coverage, astronomers could start finding systems that push that relationship toward the extreme, places where gravity says something substantial is there, while starlight has very little to say about it. And in 2026, astronomers announced one of the strangest examples yet. It is called Candidate Dark Galaxy 2. Thankfully, everyone also calls it CDG2, because repeatedly saying Candidate Dark Galaxy 2 would begin to sound less like astronomy, and more like someone reading a warehouse inventory. CDG2 sits in the Perseus galaxy cluster, roughly 300 million light-years from Earth. The Perseus cluster is not an empty region, where a small faint galaxy has managed to live quietly by itself. It is a huge collection of galaxies surrounded by hot gas and dark matter. Gravity is busy there. Galaxies move through the cluster. Some interact, some pass near one another. Gas can be stripped away. Stars can be pulled from their original galaxies. Small galaxies can be altered by the gravitational environment of larger ones. And somewhere inside this crowded region, astronomers found something that was almost missing from the picture. Not completely missing. That would have made things considerably more difficult. Instead, there were 4 small clues. 4 globular clusters. A globular cluster is a tightly packed collection of stars. Some contain hundreds of thousands of stars. They're usually old, they're usually compact, and many galaxies have populations of them orbiting around their larger stellar bodies. The Milky Way has more than 150 known globular clusters. They move around our galaxy like small, dense stellar satellites, although they are not galaxies themselves. They contain stars bound together by gravity, but they do not generally have the large dark matter halos we associate with galaxies. Now imagine looking at the Perseus cluster and finding 4 globular clusters sitting unusually close together in the sky. That by itself raises a question. Why are they together? Maybe it is chance. The Perseus cluster contains plenty of objects. Put enough stars and galaxies into one field, and eventually some things will appear close together simply because statistics enjoy causing trouble. But astronomers can calculate how likely those arrangements are. David Lee and collaborators used a statistical method to search Hubble observations of the Perseus cluster for unusual concentrations of globular clusters. They recovered 10 previously known low-surface brightness galaxies. That was encouraging. If a method is designed to find faint galaxies by looking for their globular clusters, it is helpful when it successfully finds galaxies that are already known to exist. The method also identified 2 additional candidates. One became CDG-2. At first, what stood out were the 4 globular clusters. The expected surrounding galaxy was barely there. That is a very unusual way to discover a galaxy. Usually you see the galaxy first. Then, if your observations are good enough, you identify the globular clusters around it. This was backwards. Astronomers found what looked like the accessories before they could clearly see the object they belonged to. It would be like finding 4 moons moving through space in an organised way, and only later realising there is an almost invisible planet sitting between them. The researchers needed to know whether these clusters were genuinely associated with a faint galaxy, or whether they simply happened to appear near one another. That required deeper investigation. Hubble provided extremely sharp images. Euclid provided wide, sensitive imaging that is particularly useful for detecting faint extended structures. Subaru, the large ground-based telescope in Hawaii, added further observations. Together, the 3 observatories revealed something around the 4 globular clusters. A very faint diffuse glow. Not a bright disk. Not obvious spiral arms. Not a central bulge blazing with billions of stars. Just a weak spread of starlight surrounding the clusters. That glow was the missing galaxy. CDG-2 had effectively been present in the images all along, but its stars were spread so thinly that the galaxy was extremely difficult to separate from the background. This is what astronomers mean by low surface brightness. 2 galaxies can contain similar total amounts of starlight, while looking very different if that light is distributed differently. Imagine putting 100 lamps into a small room. The room looks bright. Now take those same 100 lamps and spread them across several square kilometers. You still have 100 lamps. But any small patch of ground is receiving very little light. Astronomical objects behave similarly. A galaxy may contain millions or billions of stars, yet if those stars are spread over a large enough area, the amount of light arriving from each tiny patch of the galaxy becomes extremely low. That makes the galaxy difficult to detect against the natural brightness of the sky. Foreground light, detector noise, scattered light, and all the other things astronomers would prefer not to have in the image. A bright star is easy. A bright galaxy is easy. A faint point source can still be detected if enough photons accumulate in one small area. A faint diffuse galaxy is more troublesome because its already weak light is spread out. You are not searching for a small dim spot. You are searching for a slight change in brightness across a broad region. It is the difference between spotting a candle in a dark room and noticing that the entire wall is perhaps 1% brighter than you expected, and CDG2 is exceptionally faint. ESA described it as shining with roughly the light of about 1 million suns. That sounds like a lot until you compare it with a normal galaxy. The Milky Way contains hundreds of billions of stars. Even a small dwarf galaxy can contain millions or billions. CDG-2 appears to contain remarkably little visible stellar material for the gravitational structure associated with it. The 4 globular clusters make the situation even stranger. According to the analysis, they account for at least around 16% of the galaxy's visible light under conservative assumptions. Think about that ratio. In a normal large galaxy, globular clusters are tiny components of the overall stellar population. You can remove the Milky Way's globular clusters from a photograph, and the galaxy would still be very obviously there. With CDG2, a surprisingly large fraction of the visible light may be concentrated in just a handful of compact clusters. The background galaxy itself is barely glowing. It is almost as though most of the lights in a city had gone out, leaving only 4 unusually bright neighborhoods. That is why the globular clusters were useful. Their stars are densely packed. That high stellar density makes the clusters brighter and more compact than the faint, diffuse stellar population around them. It also makes them more resistant to some of the gravitational disruption that can remove loosely bound stars. So even when much of a faint galaxy becomes extremely difficult to detect, its globular clusters can remain visible. They become markers. Find the markers, and perhaps there is a galaxy hiding underneath. CDG2 is particularly interesting because researchers described it as the first galaxy discovered solely through its globular cluster population. That does not mean globular clusters have never helped astronomers study faint galaxies before. They certainly have. The unusual part is the sequence. The clusters led researchers to the galaxy. Then the faint diffuse light confirmed that there really was a stellar system around them. Euclid played an important role because low-surface brightness structures are exactly the kind of thing that can disappear when an instrument, observing strategy or image processing method is not optimized to preserve them. A telescope may have excellent resolution and still struggle with extremely diffuse emission. A survey may be sensitive to faint point sources while missing broad structures whose light is spread over many pixels. Image processing can also accidentally remove faint diffuse light if it is mistaken for background brightness. So detecting CDG2 was not simply a matter of taking a longer exposure. Researchers had to combine suitable observations and carefully separate the galaxy's weak signal from everything around it. Euclid's images clearly confirmed the diffuse light surrounding the globular clusters. This demonstrated another useful side of the mission. We usually talk about Euclid as a cosmology telescope. It measures galaxy shapes, it studies clustering, it maps dark matter statistically. It investigates dark energy through the expansion and growth of cosmic structure. Those are the headline goals. But when you build a telescope capable of producing sharp images across wide areas while remaining sensitive to faint extended light, it also becomes extremely useful for finding objects nobody included in the original brochure. Low surface brightness galaxies are one example. CDG2 is an extreme one. And then comes the obvious question, how much dark matter does it contain? This is where some care is needed. Astronomers have not placed CDG2 on a scale. They have not directly counted its dark matter particles. The estimate depends on relationships observed in other galaxies, particularly the connection between globular cluster populations and the masses of the dark matter halos hosting them. In many galaxies, the total number or total mass of globular clusters correlates with halo mass. The relationship is not perfect, and applying it to an object as unusual as CDG2 requires caution. But if the same relationship holds, CDG2 could be extraordinarily dark matter dominated. The detailed study estimated that dark matter could account for more than 99.9% of the system's total mass under certain assumptions. The ESA announcement used the more cautious description that about 99% appears to be dark matter. Either way, the conclusion is the same. This is not an ordinary galaxy with a slightly dimmer than average stellar population. It may be an extreme case where the halo is substantial and the visible galaxy inside it is barely present. That distinction matters because every familiar galaxy contains dark matter. The Milky Way is dark matter dominated overall. Andromeda is surrounded by a massive dark matter halo. Dwarf galaxies can contain particularly high proportions of dark matter compared with their stars, so merely saying a galaxy contains mostly dark matter is not unusual. The strange part is how little star like CDG2 seems to have produced or retained. Dark matter halos help ordinary matter gather. Gas falls into gravitational wells, the gas cools, stars form. Over time, a visible galaxy develops inside the halo. That is the simplified story. But not every halo turns its gas into stars with the same efficiency. Small halos can struggle. Gas can be heated. Ultraviolet radiation can prevent some gas from cooling. Supernova explosions can push gas outward. Galaxies passing through dense environments can lose gas. Interactions with other galaxies can disturb both stars and gas. A halo can therefore end up with far fewer stars than another halo of similar mass. CDG2 may represent an extreme outcome of those processes. Its location in the Perseus cluster may be important. A galaxy living inside a massive cluster does not enjoy a particularly quiet existence. The cluster contains hot gas spread between its galaxies. A smaller galaxy moving through that gas can experience ram pressure stripping. The effect is similar in principle to feeling air resistance while moving quickly through the atmosphere. A galaxy's stars are not usually affected strongly by this because stars are widely separated and interact mainly through gravity. Gas is different. Gas particles collide. As a galaxy travels through the intra-cluster medium, its own gas can be pushed out. Remove enough gas and the galaxy loses the raw material needed to make new stars. The existing stars remain. The dark matter halo remains, although gravitational interactions can strip portions of that too. But future star formation can decline dramatically. Tidal interactions provide another route. A galaxy passing near a much larger galaxy, or through the dense centre of a cluster, experiences differences in gravitational pull across its structure. Material in the outer regions can be removed. Repeated interactions can gradually strip stars and dark matter. A small galaxy may be altered almost beyond recognition. For CDG2, researchers have suggested that much of the ordinary gas required for star formation may have been removed through gravitational interactions in the Perseus cluster. That could help explain why the galaxy contains so little visible stellar material today. But we should not turn that into a settled biography. Nobody watched CDG2 evolve for billions of years. Researchers see its current state and use observations, simulations, and comparisons with other galaxies to reconstruct possible histories. Several processes may have contributed. Perhaps it formed stars inefficiently from the beginning. Perhaps it once contained more gas and lost it. Perhaps some stars were stripped. Perhaps the globular clusters survived because their dense structures made them difficult to disrupt. The current evidence tells us that the galaxy is extremely faint and likely highly dark matter dominated. The exact route it took to reach that condition remains part of the investigation. That uncertainty is scientifically useful. Objects such as CDG2 test our ideas about galaxy formation. A successful theory does not only need to create Milky Ways, it has to explain the strange systems too. Bright spirals, giant ellipticals, tiny dwarf galaxies, ultra-diffuse galaxies, galaxies rich in gas but poor in stars, galaxies that appear to contain surprisingly little dark matter, and galaxies like CDG-2 that may contain almost nothing except dark matter and a very small stellar population. Nature rarely provides one standard model and politely produces copies. The variety is part of the test. Consider how odd CDG-2 would look if human eyes could somehow see dark matter. Right now, the visible image is nearly empty. 4 compact globular clusters stand out. A faint diffuse patch surrounds them. Most of the object seems absent. But if dark matter were luminous, the picture might change completely. Instead of a weak smudge, perhaps you would see a much larger halo dominating the region. The stars would appear as a small decoration inside it. The object would stop looking like a nearly failed galaxy and start looking like a substantial dark structure that happens to contain very little visible material. Of course, we cannot see dark matter this way. That is exactly the problem. We are forced to judge galaxies by the minority component that produces light. CDG-2 makes that bias obvious. It looks insignificant because we are looking with photons. Gravity may tell a different story. This also connects back to the dark subhalos predicted by simulations. Cold, dark matter models produce many halos and subhalos. Not all of them are expected to form bright galaxies. The smallest halos may contain few or no stars. Larger ones may remain extremely faint. Finding those systems is difficult because astronomy traditionally discovers galaxies through starlight. If a halo makes almost no stars, it removes the easiest detection method. This has created a long-standing observational challenge. Simulations can show dark matter structures directly because the computer knows where the simulated dark matter particles are. The real universe does not give astronomers that option. We need tracers. Globular clusters may provide one. Gravitational lensing provides another. Gas detected at radio wavelengths can sometimes reveal systems with very few stars. Stellar streams can expose gravitational disturbances. The motion of nearby objects can imply an unseen mass. Each technique approaches the dark population from a different direction. CDG-2 suggests that searching for unusual globular cluster groupings may uncover galaxies that ordinary surveys overlook, and once one method begins working, you can apply it repeatedly. The original search recovered known low-surface brightness galaxies. It found 2 additional candidates. One has now received strong support as a genuine galaxy through the combined Hubble, Euclid and Subaru observations. There may be more, probably not millions of identical CDG-2 systems waiting politely for the next catalogue release. Extreme objects are extreme for a reason, but even a modest population would matter. How common are almost dark galaxies? Do they mostly live in clusters? Do they form in isolation too? Are they ordinary dwarf galaxies that lost their gas and stars? Were they inefficient at forming stars from the beginning? How massive are their halos? Do their globular cluster populations follow the same relationships found in brighter galaxies? And at what point does an extremely dark galaxy stop being a galaxy and become a dark halo containing a few stars? That last question sounds philosophical, but it has a practical side. Astronomers need definitions. A galaxy is generally a gravitationally bound system containing stars, gas, dark matter, or some combination of these components. But once the visible population becomes tiny, the distinction between a faint galaxy, a star cluster, and a dark halo becomes difficult observationally. Globular clusters themselves are gravitationally bound collections of stars. They usually lack substantial dark matter halos. Dwarf galaxies may contain similar numbers of visible stars but sit inside dark matter halos. So measuring the surrounding mass is crucial. 2 objects can look similarly faint while being physically very different. One may simply be a star cluster. The other may be the visible centre of a much larger dark matter structure. CDG2 appears to belong to the second category. Its diffuse stellar light supports the interpretation that the four globular clusters are part of a larger galaxy. The possible halo mass makes the object much more extreme. That is why calling it almost dark is more accurate than calling it completely dark. There are stars. We see them. There is diffuse light. Euclid helped detect it. The galaxy is faint, not invisible. A truly dark galaxy containing no stars at all would be much harder to confirm. Without stars, there would be no optical galaxy to photograph. You might detect gas if gas were present. You might see gravitational lensing. You might notice effects on nearby objects. But proving that an unseen halo exists and determining whether it should be considered a galaxy would become considerably more difficult. CDG2 sits close to that observational boundary, while still giving astronomers something visible to work with. 4 globular clusters, a faint background population, just enough light to reveal the larger system, and that makes Euclid particularly well suited to surching for more examples. Wide surveys are important because rare objects require large search areas. Sensitivity to low surface brightness is important because the diffuse stellar component can otherwise vanish into the background. Sharp imaging helps distinguish compact globular clusters and small structural details. Measurements from other telescopes can then add information at different wavelengths or higher resolution. Euclid does not replace Hubble. Hubble does not replace Subaru. Subaru does not replace Euclid. The CDG2 result needed their strengths to work together. Hubble's high-resolution images helped identify the tight group of globular clusters. Euclid's data clearly confirmed the faint diffuse galaxy around them. Subaru added independent ground-based observations. The unusual object became convincing because several instruments saw compatible pieces of the same system. That is how modern astronomy often works. The dramatic headline may mention one telescope. The real result arrives through a small committee. And CDG2 gives us another reason to be cautious with the phrase, where dark matter hides. Dark matter is not deliberately hiding inside faint galaxies. It surrounds bright galaxies too. It fills clusters. It traces filaments. It contributes to the entire cosmic web. What changes with CDG2 is the balance between dark matter and starlight. In a normal galaxy, the visible component gives us an obvious signpost. In CDG2, the signpost is nearly gone. The halo may be there in abundance, while the stars provide only a weak clue. That makes the invisible structure easier to appreciate conceptually because the usual distraction has been removed. Very little light, potentially a great deal of mass. The galaxy becomes an extreme demonstration of something Euclid is discovering everywhere else more indirectly. Starlight is not a reliable measure of how much matter occupies a region. A bright galaxy can sit inside a massive halo. A faint galaxy can also sit inside a massive halo. Two systems with similar amounts of dark matter can potentially produce very different amounts of visible light depending on how their gas and stars evolved. That means mapping galaxies and mapping matter are related problems, but they are not identical. Euclid needs both. Its galaxy survey tells researchers where luminous structures are. Weak lensing tells them how total mass is distributed. Objects like CDG2 remind us why comparing those two maps is so important. Sometimes the galaxies trace the dark matter clearly. Sometimes the visible object is surprisingly faint. Sometimes environmental processes alter the relationship. And if Euclid collects enough examples, scientists can measure how often these mismatches happen instead of treating each one as a curiosity. That broader sample could help answer several questions that remain open. How efficiently do dark matter halos turn ordinary gas into stars? How much material is stripped when a galaxy enters a cluster? How well does globular cluster abundance trace halo mass at the faintest extremes? Are there many dark halos containing only tiny stellar populations? Do current galaxy formation simulations produce enough systems like CDG2? And if they do not, is the problem in our understanding of star formation, environmental stripping, dark matter, or some combination of all three? CDG2 does not answer those questions by itself. It makes them harder to ignore. That is often how a useful discovery works. It does not arrive with a label saying, "Mystery solved." It gives researchers an object that forces several existing ideas to face the same measurement. And Euclid is only beginning to produce the survey needed to find more cases. As the picture becomes more precise, scientists will be able to ask a more difficult question than simply where the dark matter is. They will be able to ask whether it is behaving exactly the way our current model says it should. And that is really where Euclid has reached now. Not at the point where dark matter has been identified in a laboratory. Not at the point where someone can hold up a detector reading and say, "There it is. That particle is dark matter." Euclid was never designed to do that. Its job is different. It is building a much larger picture of where matter is distributed, how galaxies sit inside that distribution, how the structure changed over billions of years, and whether the patterns match the universe described by our current theories. The early results are already showing that the telescope can do those things. It can measure enormous numbers of galaxies. It can find strong gravitational lenses. It can measure weak lensing. It can trace clusters. It can reveal very faint galaxies. It can identify structures associated with the cosmic web. And around Abel 2390, Euclid data have now been used to reconstruct a mass distribution dominated by dark matter. That last result is especially important because weak gravitational lensing is one of the mission's main tools for studying cosmic structure. The telescope was designed around the assumption that astronomers could measure tiny distortions in enormous populations of background galaxies and use them to trace matter that does not emit light. Abel 2390 showed that the real instrument, operating in real space, looking at real galaxies, can produce the measurements needed to make that work. That may sound less dramatic than discovering an entirely new kind of particle. It is also the sort of result scientists need before they can trust the much larger measurements that come later. A survey this ambitious depends on tiny effects. If the telescope measured galaxy shapes slightly incorrectly, that would matter. If distances were systematically biased, that would matter. If the optical system introduced small distortions that were mistaken for gravitational lensing, that would definitely matter. You do not want to spend 6 years mapping a feature of the universe only to discover that part of the universe was actually a camera problem. So the early observations are doing more than producing interesting discoveries. They are testing the machinery of the experiment. Can Euclid distinguish stars from galaxies? Can it preserve faint extended light? Can it measure tiny galaxy shapes? Can researchers estimate redshifts accurately enough? Can the data processing pipelines handle millions and eventually billions of objects? Can independent analysis methods recover the same signal? So far the answers have been encouraging. The first public survey release in March 2025 covered 63.1 square degrees across Euclid's deep fields at approximately the depth of a normal wide survey visit. That is a large area for a high-resolution space survey. It is still tiny compared with the mission's eventual goal. The 3 mosaics contained around 26 million galaxies. Some of those galaxies are relatively nearby. Others are so distant that their light began travelling toward us when the universe was much younger. The farthest ordinary galaxies in those early mosaics were seen at distances corresponding to more than 10 billion years of light travel time. 26 million galaxies from a preview. That gives some idea of why astronomers keep describing Euclid as a survey machine. The goal is not simply to discover one extraordinary object. It is to collect enough ordinary objects that the statistics become extraordinary. And even within those early fields, unusual things began appearing. Hundreds of strong gravitational lens candidates were identified. Galaxy clusters appeared. Faint dwarf systems were studied. Stellar streams became visible. Large-scale filaments could be traced. Active galactic nuclei and quasars appeared in enormous numbers. Researchers began classifying galaxy shapes and structures. Then there were objects such as CDG2, where an almost invisible galaxy became noticeable because of a small group of globular clusters. This is the useful side effect of building a telescope for cosmology. To measure the universe statistically, you first have to photograph an enormous amount of it very well. That creates a dataset useful for almost everything sitting inside those images. Euclid is supposed to study dark matter and dark energy. It also happens to notice whatever else is in the way: stars, asteroids, quasars, galaxy mergers, faint streams, rare lenses, dwarf galaxies. Objects that may not have been expected when the spacecraft was designed. Give astronomers a wide, sharp map of the sky, and they will find reasons to examine nearly every pixel. By June 2026, Euclid had produced a second quick public release as well, although it was very different from the first. Instead of looking primarily at distant extragalactic fields, Euclid had temporarily pointed toward the crowded bulge near the centre of our own Milky Way. The result covered 4.8 square degrees and catalogued around 60 million stars. That observation is not part of the main dark matter mapping program. It demonstrates something else about the telescope. Euclid can handle extraordinary source density. Looking toward the galactic bulge is almost the opposite of the normal cosmological survey. For dark universe work, astronomers prefer areas away from the Milky Way's crowded plane, so distant galaxies can be measured cleanly. Near the galactic centre, the field is packed with stars. Yet Euclid's instruments and data processing system were able to turn that crowded view into a massive stellar catalogue. The main cosmological work continues elsewhere, and the most important data release for the mission's central scientific questions is still ahead. Euclid began its main cosmological survey on February 14, 2024. The first major release based on roughly a year of survey observations, known as Data Release 1, is scheduled for late 2026. That release is expected to be fundamentally different from the quick releases we have seen so far. The early releases were previews. They allowed scientists to test the data. They showed what Euclid could do. They provided enormous value for other areas of astronomy. But they were not the main cosmology result. DR1 is expected to begin delivering the scale of dataset needed for Euclid's central mission. The Euclid Consortium describes it as set to become the largest map of the universe ever produced from space in both visible and infrared light. Not the deepest image ever taken. Those are different things. A telescope such as Webb can look extremely deeply into carefully selected regions. Euclid's strength is area combined with high-resolution space imaging. Think of the difference between photographing one street with extraordinary detail and surveying an entire country at very high resolution. Both images can be excellent. They answer different questions. Cosmology needs the country. Actually, cosmology would prefer several countries, a few continents, and perhaps the entire planet if someone can arrange the observing time. Euclid's wide survey is designed to cover roughly 14,000 square degrees. The entire sky contains a little over 41,000 square degrees, so Euclid is aiming at roughly 1/3 of the celestial sphere. That is not an arbitrary fraction. Large areas near the Milky Way are poor choices for the main survey, because our own galaxy fills those directions with foreground stars and dust. The plane of the solar system also produces additional background light from interplanetary dust. Euclid concentrates on the cleaner parts of the sky where distant galaxies can be measured most effectively. A typical wide survey pointing covers about 0.57 square degrees. Euclid observes the field in visible and near-infrared light, makes several slightly shifted exposures, obtains spectroscopic information, then moves on. And then it does it again, and again. For years. A single field is interesting. Thousands of fields become the map. That map will contain the positions of galaxies across enormous distances. It will contain shape measurements for huge populations of background galaxies. It will contain redshifts for millions of galaxies. It will reveal clusters. It will trace filaments. It will allow researchers to compare the visible galaxy distribution with the mass distribution inferred through lensing. Most importantly, It will cover enough volume that scientists can divide the universe into different periods of its history. This is the part that turns a map into an experiment. Suppose Euclid only mapped dark matter today. That would still be valuable. But one snapshot cannot tell you exactly how quickly the structure developed. Euclid looks across distance. And because light takes time to travel, different distances correspond to different cosmic ages. The nearby universe shows a structure after almost the full history of cosmic development. Distant galaxies show earlier stages. Farther still, the universe was younger again. Place those observations together and researchers can examine the growth of structure. How quickly did dark matter halos grow? When did massive clusters become common? How did matter flow into filaments? How did voids become emptier? Did the rate of growth slow when accelerated cosmic expansion became important? Those changes depend on gravity. They depend on dark matter. They depend on the expansion history. And they may depend on whatever dark energy actually is. That is why Euclid's dark matter map cannot be separated completely from the dark energy problem. Dark matter helps structure form. Gravity pulls matter into denser concentrations. Dark energy, according to the standard cosmological picture, is associated with the accelerated expansion of the universe. As expansion accelerates, distant structures are increasingly separated. Gravity still works locally. Galaxies do not suddenly fly apart because dark energy has entered the room. But the large-scale growth of structure is affected by the expansion history. Measure that growth precisely enough, and you gain information about both. Euclid will use several methods together. Weak lensing measures how total matter distorts distant galaxy shapes. Galaxy clustering measures how galaxies are distributed through three-dimensional space. Baryon acoustic oscillations provide a statistical standard ruler left over from conditions in the early universe. Redshift space distortions reveal how galaxy motions respond to gravitational structure. These are different measurements. That is useful. A strange result seen through only one method may be caused by a problem specific to that method. A strange result appearing independently in several methods becomes much more interesting. Suppose weak lensing suggests matter has clumped less strongly than expected. Researchers would ask whether galaxy shapes were measured correctly, whether galaxy distances were accurate, whether intrinsic alignments had been modelled properly, whether instrument effects had been removed. Then suppose galaxy clustering independently points toward the same mismatch. Now the conversation changes. Perhaps the model needs adjustment. Perhaps dark energy evolved differently. Perhaps gravity behaves differently on cosmic scales. Perhaps some property of dark matter affects structure formation. Or perhaps there is another observational complication nobody had appreciated. The first response in cosmology is usually not to throw Einstein out of the building. Einstein has survived enough attempted evictions to deserve some procedural fairness. But precise surveys are built precisely because even successful theories should be tested. The standard model of cosmology, often called lambda cold dark matter, or lambda CDM, describes an enormous range of observations surprisingly well. The cold dark matter part supplies the dominant matter component responsible for much structure formation. Lambda represents the cosmological constant, the simplest explanation for dark energy. Add ordinary matter and radiation, and the model can reproduce much of the universe we observe. It explains patterns in the cosmic microwave background. It describes the large-scale distribution of galaxies. It predicts how structure should grow. It gives us a consistent history from a hot early universe to the network of galaxies we see today. And yet its two dominant late-time ingredients have awkward names. Dark matter, dark energy. Those names are basically admissions. Something produces these effects. We can measure those effects. We can model them. We do not know what the underlying physics ultimately is. Dark matter has not been directly identified as a particle. Dark energy may be a cosmological constant, a new field, a feature of gravity, or evidence that some part of our description is incomplete. Euclid exists because the next step is precision. Measure the structure more accurately. Measure the expansion more accurately. Compare the two. Look for disagreement. A major result could be a clear deviation from lambda CDM, but a major result could also be the opposite. Imagine Euclid completes its survey. Weak lensing agrees with galaxy clustering. Structure grows at the predicted rate. The dark matter distribution matches simulations. Dark energy behaves consistently with a cosmological constant. General relativity continues working across enormous scales. Nothing breaks. That would not make Euclid a failure. It would narrow the possibilities dramatically. The universe would be telling us that whatever dark matter is, and whatever dark energy is, their large-scale behavior follows the existing model with remarkable precision. Particle physicists would still need to identify dark matter. Theorists would still need to explain dark energy, but they would have fewer places to hide their alternatives. Precision removes possibilities. That is part of discovery too. There are already smaller tensions in cosmology that make these measurements especially interesting. Different methods of estimating certain cosmological quantities do not always agree perfectly. Researchers continue debating whether some disagreements are statistical accidents, hidden systematic errors, or signs that the standard model needs modification. Euclid is not guaranteed to settle every one of these questions. No single mission could, but it adds something very valuable. A huge, carefully controlled dataset designed specifically to connect geometry and structure. The telescope measures where galaxies are. It measures what shapes they appear to have. It helps estimate how far away they are. From those simple ingredients comes one of the most ambitious maps humans have attempted. Not a map of planets, not a map of stars, a map of the large-scale matter distribution across a substantial portion of the observable universe and across much of cosmic history. And building that map is not merely a matter of joining photographs together. Raw data leave the spacecraft and travel back to Earth. Processing centers calibrate the images, instrument signatures are removed. Objects are detected, measurements from visible and infrared instruments are combined. Ground-based observations add wavelength coverage. Spectra are analysed. Redshifts are determined. Galaxy shapes are measured. Catalogues are checked. Artificial sources and simulations are used to test biases. Independent teams compare results. Only after those steps can the cosmological analysis begin. The map is therefore partly an astronomical achievement and partly a computing achievement. Billions of sources are too many for astronomers to inspect one by one. Nobody has a notebook large enough. Automated pipelines are necessary. Machine learning helps with certain classification tasks. Simulations provide controlled datasets for testing. Citizen scientists have even contributed to the identification of gravitational lenses. The telescope takes the observations, but the finished scientific map is produced by a network of people and machines spread across Earth. That seems appropriate for a mission trying to reconstruct a network spread across the universe. The final product will not look like a normal atlas. There will be images, certainly. There will be beautiful mosaics. But the real scientific map exists in catalogues, probability distributions, redshift measurements, lensing shear fields, mass reconstructions, correlation functions, and three-dimensional positions. A picture may show thousands of galaxies. The underlying dataset tells researchers how those galaxies relate to one another. That is where the dark universe becomes measurable, and by mid-2026, Euclid is still near the beginning of that process. The impressive images we have seen are not the completed survey. The weak lensing reconstruction around Able 2390 is not the finished dark matter map. CDG2 is not the answer to what dark matter is. The Einstein rings are not the mission's final result. They are early examples of what the observatory can find while the much larger survey accumulates. The major cosmological results are still coming. which means the most honest conclusion at this point is not that Euclid has solved dark matter. It has begun building the dataset that can tell us whether our current description of the dark universe survives one of its most demanding tests. And the map will keep growing long after any single discovery has left the headlines, field by field, galaxy by galaxy, until isolated clusters, halos, lenses, filaments and voids begin to fit together into one much larger view. What might that map eventually tell us? Possibly that our current picture is remarkably close to correct. Possibly that something important is missing. At the moment, both possibilities remain open. That is an easy detail to lose whenever a new Euclid result appears with words such as dark matter, invisible universe, hidden galaxy, or cosmic web attached to it. The images are impressive. The headlines sound final. The science is still developing. Euclid has not discovered a dark matter particle. It has not shown that dark matter lives only in one particular type of object. It has not replaced every previous dark matter measurement. What it is doing is much broader. It is changing the scale at which the invisible matter distribution can be measured from space. For decades, astronomers assembled the dark matter picture through individual clues. Galaxies rotated too quickly. Clusters contained too little visible mass. Gravitational lensing revealed additional gravity. Colliding clusters separated hot gas from much of the gravitational mass. Simulations showed that an unseen matter component could build the large-scale structure we observe. The evidence came from different objects and different methods. Euclid adds something new to that history. Consistency across an enormous survey. The same telescope, the same instruments. The same observing strategy. Applied again and again across a large fraction of the extragalactic sky. That uniformity is important. Imagine trying to understand population statistics using measurements collected with thousands of different rulers, some slightly longer than others. You could correct for the differences. Scientists do this constantly when combining observations from different telescopes. But a huge survey made with one stable instrument gives you a much cleaner foundation. Euclid can compare distant galaxies in one part of the sky with distant galaxies somewhere else using the same basic measurement system. It can compare structures at different distances. It can examine galaxy populations over huge volumes. Then other observatories can add information rather than carrying the full burden of making the survey consistent. By the end of the nominal mission, Euclid's wide survey is intended to cover around 14,000 square degrees. Its deep survey covers a much smaller area but revisits those fields many times, eventually reaching much fainter objects than a normal wide survey observation. Those deep fields serve several purposes. They help with calibration. They allow astronomers to study fainter populations. They make it possible to compare repeated observations. They also give Euclid a set of regions where the universe is examined much more deeply, while the wide survey provides the enormous area. It is the same basic trade-off we have seen throughout the mission. Depth tells you more about a smaller piece. Width tells you how representative that piece really is. Euclid uses both. By 2025, a single early pass through the deep field regions had already revealed around 26 million galaxies. Those observations covered only 63 square degrees. As Euclid revisits the deep fields dozens of times, fainter galaxies will emerge. Objects that are barely detectable in one visit become measurable when observations are combined. Rare events may appear. Variable sources can be compared across time. Distant galaxies that initially sit near the limit of detection become part of larger statistical samples. Meanwhile, the wide survey continues moving through new regions. There is a nice practical contrast here. The wide survey behaves like someone trying to inspect every room in a very large building. Open the door, look carefully, record everything, move to the next room. The deep survey behaves like someone who finds 3 rooms particularly interesting and keeps coming back with better lighting. Both approaches teach you something different, and the building in this example happens to contain billions of galaxies. When the first major cosmology release arrives, researchers will begin applying the methods Euclid was designed around to a much larger dataset. Weak gravitational lensing will reveal statistical patterns in total matter. Galaxy clustering will reveal how visible galaxies occupy three-dimensional space. The comparison will test how well galaxies trace the underlying dark matter framework. The redshift information will divide those measurements by cosmic time. That should allow researchers to watch the large-scale structure grow, not literally as a movie. The universe has not kindly supplied time-lapse footage. Different distances show different eras. Astronomers reconstruct the development by comparing them. Imagine looking at photographs of forests of different ages. One field contains seedlings, another young trees, another mature woodland. You're not watching one forest grow. But by comparing many examples at known ages, you can infer how forests develop. Euclid does something roughly comparable with cosmic structure. Nearby regions show a later universe. Distant regions show earlier versions. The difference tells researchers about growth. If that growth agrees with lambda CDM, confidence in the model increases. If it does not, the pattern of disagreement matters. Perhaps structures form normally at early times and then diverge later. That might point toward the expansion history. Perhaps differences depend on physical scale. That could suggest something about gravity or dark matter behavior. Perhaps galaxy clustering disagrees, but lensing does not. Then researchers may look closely at the way galaxies occupy halos. There is no single possible surprise. This is why broad, precise surveys are so valuable. They do not test one number. They test a network of relationships. And dark matter itself still presents the largest unresolved question. What is it? We have spent this entire journey talking about where dark matter gathers without answering what the material actually consists of. That may feel slightly unfair. It is also an accurate description of modern physics. Astronomers can measure the gravitational mass of a galaxy cluster. They can reconstruct a halo. They can map cosmic structure. They can compare those structures with computer simulations, yet the underlying particle remains unknown. The simplest cold dark matter model assumes the substance moves relatively slowly compared with light during the period when structures are forming and interacts only weakly with ordinary matter beyond gravity. That broad behavior works extremely well cosmologically. But many different particles could potentially behave that way. Physicists have proposed WIMPs, axions, ultralight particles, sterile neutrinos, more complicated hidden sector particles, and numerous other possibilities. Experiments have searched underground. Particle accelerators have searched through high-energy collisions. Astronomers have looked for possible radiation signatures. No candidate has yet become the accepted answer. Euclid approaches the mystery from the structure side. Different dark matter models can produce subtle differences in the number, shapes, and internal structures of halos. Some may suppress small-scale structure. Some may create different halo centers. Self-interacting dark matter could alter density profiles or behavior during collisions. Warm dark matter would change how efficiently small halos form. Ultralight dark matter could affect structure below characteristic scales. Euclid may not distinguish every model by itself. Its observations can provide constraints. Combine those constraints with strong lensing studies, stellar streams, dwarf galaxies, laboratory searches, cosmic microwave background measurements, and other astronomical surveys, and the allowed possibilities become narrower. Science often advances this way. Not through one instrument walking into the room with the answer, through several instruments gradually closing the exits. Dark energy presents a different mystery. Unlike dark matter, dark energy does not gather into obvious halos. Its main signature is the accelerating expansion of the universe. The simplest model treats it as a cosmological constant. That would mean its energy density remains constant as space expands. It is mathematically straightforward. Physically, it raises difficult questions. The observed value is extraordinarily small compared with naive estimates from quantum physics. Why it has this value is unknown. Why dark energy became cosmologically important during the era when galaxies and observers exist is another question. Maybe the cosmological constant really is the answer. Maybe dark energy evolves. Maybe our theory of gravity needs modification on the largest scales. Euclid cannot assume the answer. It measures the consequences. How did distances change? How quickly did structure grow? Do the two histories agree with general relativity plus a cosmological constant? If yes, another large region of theoretical possibility disappears. If no, the details will determine what comes next. And this is why calling Euclid simply a dark matter telescope misses half the story. Its subject is the geometry and structure of the universe. Dark matter and dark energy are inferred through those measurements. They are connected because the expansion history influences structure growth. Euclid measures both sides of the relationship. One of the quiet strengths of this approach is that it does not require the dark components to reveal themselves directly. Dark matter may refuse to produce detectable light. Dark energy may not be a material substance at all. No problem. Measure galaxies, measure distances, measure shapes, measure clustering. Measure how those patterns change. Then ask what kind of universe could have produced them. That approach has taken us from a simple image of the night sky to something much stranger. When you first look upward, the stars seem to be the universe. Then telescopes reveal galaxies. Infrared instruments reveal objects hidden by dust. Radio telescopes reveal cold gas. X-ray observatories reveal hot plasma and black hole environments. Gravitational wave detectors reveal mergers that may be invisible to ordinary telescopes, and gravitational lensing reveals mass that produces no light at all. Each new method changes what the word visible really means. Euclid belongs to that tradition. It is a telescope using light to study something that light does not show directly. The galaxies are the measuring grid. Their shapes are the clues. Their positions provide the pattern. Their redshifts add distance. Gravity connects the visible measurements to the invisible mass, which brings us back to the beginning. We started with the strange idea of building a telescope to see something that cannot be seen. The contradiction disappears once we understand the method. Euclid is not trying to photograph dark matter. It is photographing the universe around it accurately enough that dark matter cannot avoid affecting the result. A halo bends background light. A cluster distorts thousands of galaxies. A filament contributes to cosmic shear. A faint galaxy moves inside an invisible gravitational environment. A stellar stream follows a path shaped by mass. An Einstein ring records the gravity of the foreground lens. The evidence changes form, but gravity keeps repeating the message. There is more here than the light suggests, and maybe that is the most useful way to think about Euclid's map. It is not an image of darkness. It is a measurement of everything the darkness has done to the visible universe. By the time the survey is complete, the map will contain a history stretching across billions of years. Some regions will show the universe when large structures were still growing quickly. Others will show clusters at later stages. The distribution of galaxies will mark the web. Weak lensing will trace matter between the bright markers. The deep fields will extend farther into the past. The wide survey will provide the statistical scale needed to distinguish unusual objects from common behavior. And all of those pieces will eventually be compared with simulations. Researchers can create model universes containing different amounts of matter, different dark matter properties, different dark energy behavior, different assumptions about gravity. Then they can ask which simulated universe produces statistics most like Euclid's real one. Perhaps one familiar model fits everything. Perhaps several survive. Perhaps none do. That last possibility would be the most exciting and also the most inconvenient. Physicists generally enjoy discovering that something is wrong with a theory. They enjoy it slightly less when the theory is the one they need to explain almost everything else. Still, that is what observations are for. A scientific theory is not protected because it has been successful. It remains successful only as long as new measurements continue agreeing with it. Euclid is one of those new measurements, a very large one, and its influence will not end when the nominal survey ends. Astronomical datasets have long lives. Hubble observations taken decades ago are still being analysed today. Old sky surveys continue producing discoveries because new techniques reveal information researchers were not originally searching for. Euclid's catalogue will be enormous. Future astronomers may use it for questions that have not yet been invented. New dark matter theories can be tested against it. New galaxy formation models can be compared with it. Objects that seem unimportant today may become crucial when another telescope discovers a related class years from now. The mat becomes part of astronomy's memory. Other major observatories will add their own views. The Vera C. Rubin Observatory will repeatedly survey the southern sky from the ground, tracking changes over time and measuring enormous populations of galaxies. NASA's Nancy Grace Roman Space Telescope will provide wide-field infrared observations with different capabilities. Webb will continue studying selected distant objects in extraordinary detail. Ground-based spectroscopy will add redshifts. Radio telescopes will trace gas. X-ray observatories will examine hot cluster material. Gravitational wave experiments will investigate entirely different messengers. Euclid fits into this network rather than standing alone. One telescope gives breadth, another gives depth, another gives time coverage, another gives a different wavelength. Put them together and the universe becomes harder to hide. Not easy to understand, just harder to hide. And perhaps dark matter will remain unidentified after Euclid completes its survey. That possibility is real. The telescope may tell us where the matter is with extraordinary precision, while still leaving its particle identity unknown. That would be frustrating. It would also be progress. Knowing exactly how dark matter is distributed constrains what it can be. Knowing how structure grows constrains its behaviour. Knowing halo shapes constrains interactions. Finding dark substructure constrains particle properties. Every observation reduces the space of possible answers. Maybe eventually one candidate survives them all. Or perhaps an unexpected pattern forces us to rethink the question entirely. For now, Euclid continues looking. It circles the Sun with Earth from its distant operating region near L2. Roughly 1.5 million kilometers away from us. Its mirror collects photons, its detectors record galaxies, the spacecraft sends those measurements home. Most of the galaxies do not become famous. Nobody gives them names. Nobody makes a documentary about galaxy number 418,725,391. And yet those ordinary galaxies are exactly what makes the mission powerful. Each contributes a small amount of information, one shape, one position, one distance, one tiny lensing distortion. Individually, almost nothing. Together, a map. And somewhere tonight, depending on where you're listening, the sky above you contains a small portion of that same structure. You may see a few stars, perhaps a planet. Maybe the moon is bright enough to wash out everything else. Behind those nearby lights are distant galaxies that your eyes cannot detect. Around those galaxies are dark matter halos. Between the clusters are filaments. Beyond the filaments are voids. And through all of it, light is travelling toward us carrying tiny records of the gravity it encountered along the way. Euclid is collecting those records. That does not make the darkness visible in the ordinary sense, but it does make it measurable. And after everything we have followed, from galaxies rotating too quickly, to giant clusters bending light, to Einstein rings, hidden halos, the cosmic web, and an almost dark galaxy with only a handful of bright clues, we can finally answer the question in the title a little more carefully. Where does dark matter really hide? Almost everywhere structure exists, around galaxies, inside clusters, along the cosmic web, in small halos that may contain few stars, in enormous concentrations that shape the motions of thousands of galaxies. It is not hidden because it found a particularly clever location. It is hidden because our eyes are built for light, and dark matter apparently is not interested in light. Gravity is the reason we know it is there. Euclid is giving us a way to follow that gravity across a large part of the universe, and while the final map is still being built, the early pieces already show what the telescope can do. So perhaps before you drift completely away, think back to that first question. Where are you listening from tonight? Maybe your room is quiet now. Maybe the screen has dimmed. Maybe you've made it much farther through the universe than you originally intended. Wherever you are, you're sitting inside the Milky Way's dark matter halo, on a planet orbiting one star among hundreds of billions, inside a galaxy moving through a much larger network of matter that stretches far beyond anything visible in the night sky. And if this long journey through Euclid's invisible universe has helped you unwind, you can leave a like, subscribe to Science for Sleep, and share it with someone who might enjoy falling asleep somewhere between a galaxy halo and a cosmic filament. There will be much more to learn as Euclid's survey grows. The first major cosmology datasets are only beginning to arrive. The full map will take years. And the question of what dark matter actually is may take longer still. For tonight, though, we can leave the telescope to continue its work. One field at a time, one galaxy after another, measuring light, following gravity, and slowly filling in the parts of the universe that our eyes were never able to see. Sleep well, fellow traveller, wherever in the cosmic web you happen to be.